Hello there, and welcome to Science for Sleep, a place where curiosity gets comfortable, questions take their time, and learning is allowed to slow down just enough for your thoughts to soften. Wherever you're listening from tonight, whether the lights are already low or the world outside your window is still busy, I'm glad you're here. This little corner of science is designed not to rush you, not to impress you, and certainly not to keep you awake on purpose. It's simply here to wander gently through big ideas, one calm step at a time. Tonight we're exploring a question that seems simple on the surface, but grows more interesting the longer you sit with it. We've been to the moon. Humans walked there more than half a century ago. We planted flags, drove small vehicles, collected rocks, and came home safely. And yet Mars, a planet that has captured our imagination for generations, still remains untouched by human footsteps. So why is that? Why does a dusty red world that looks, at least from afar, like a cold desert, feel so much harder to reach than a place we already visited decades ago? You might find yourself wondering this casually, maybe after seeing a headline about a new Mars rover, or watching old footage of Apollo astronauts bouncing across the lunar surface. If we could do that in the 1960s and 70s, with computers less powerful than a modern wristwatch, what's stopping us now? Is it technology? Is it money? Is it danger? Or is there something deeper about distance, time, and the kind of journey Mars actually demands from us? Before we settle into that question, let me ask you something gently, the way we often do here. Where are you listening from tonight? Are you stretched out in bed, sitting on a quiet couch, or drifting somewhere between the two? And what time is it for you right now, in your own small corner of Earth? It's fitting in a way to think about time and place while talking about space, because those ideas are far more connected than they first appear. If you find this calm exploration soothing, or if it helps your mind unwind after a long day, you're always welcome to like the video or subscribe to this channel. It helps this slow, thoughtful approach to science reach others who might need a gentle pause too. There's no rush though. Nothing here is urgent. We have plenty of time. So let's begin, not with Mars itself, but with something much closer, something familiar, and something that still feels extraordinary when you really think about it. Let's begin with the moon. The moon feels close to us in a way few other objects in the universe do. It hangs in the sky, large and steady, changing its shape night after night in a rhythm we instinctively recognize. Long before rockets and radios, humans tracked time by its phases. It guided travelers, inspired stories, and quietly reminded us that there was more beyond the ground beneath our feet. When we finally decided to go there, it felt like the next logical step, even though it was anything but easy. When Apollo 11 landed on the moon in 1969, it wasn't just a technological triumph. It was a statement about what humans could do when they focused their energy, resources, and attention on a single goal. The journey took about 3 days. 3 days from Earth to the lunar surface. That's roughly the length of a long weekend. If something went wrong, the astronauts could turn around and come home. Communication with Earth was nearly immediate. Mission Control could speak to the crew in real time, offer guidance, and respond to problems as they happened. That closeness mattered more than most people realize. The moon was far enough to feel bold and historic, but close enough to remain connected to Earth in a very practical way. It was, in cosmic terms, just across the street. Now, Mars does not work that way. Mars is not simply farther away in distance. It is farther away in commitment. It asks for time in a way the moon never did. Travelling to Mars is not a 3-day journey. It is a voyage that takes months just to get there, followed by months spent waiting on the surface, followed by months more to return home. And all of that depends on the planets lining up just right, something that only happens every couple of years. That alone changes the nature of the mission completely. A trip to the moon is an expedition. A trip to Mars is relocation, even if temporary. You don't pack for Mars the way you pack for the moon. You don't think in terms of quick fixes or emergency returns. Once you leave Earth for Mars, you are committed to seeing it through. This difference often gets overlooked because we tend to think of space travel as simply a matter of speed. Faster rockets, better engines, stronger materials. But the real challenge is not how fast you can go. It's how long you can survive while going nowhere in particular, sealed inside a small spacecraft millions of kilometers from home. On the way to the moon, astronauts could look out a window and see Earth growing smaller, but never disappearing. It was always there, a bright blue anchor in the blackness. On the way to Mars, Earth eventually becomes just another star. A familiar one perhaps, but no longer a place you can reach quickly. That psychological shift alone is enormous. And this is where the phrase, "we've been to the moon," can become misleading. It makes it sound like Mars is just the same thing, only a bit farther. In reality, Mars is not the next step on the same staircase. It's a different staircase altogether. To understand why, it helps to think about space not as an empty highway, but as a constantly moving system. Earth and Mars are both orbiting the Sun, each at its own speed, along its own path. Sometimes they are relatively close to each other, at least by planetary standards. Other times they are on opposite sides of the Sun, separated by hundreds of millions of kilometers. You can't just leave whenever you want and go straight there. You have to wait for the right alignment, the right window, when the energy required to travel is at its lowest. These launch windows don't open often. Roughly every 26 months, Earth and Mars line up in a way that makes travel practical. Miss that window, and you're waiting more than 2 years for the next chance. That kind of timing pressure adds layers of complexity to every decision. Supplies, crew health, mission duration, and even political will all have to align with celestial mechanics that do not care about our schedules. The moon doesn't impose that kind of patience. You can go to the moon almost any time. Mars insists that you plan your life around it. Then there's the matter of landing. This might seem counterintuitive at first, but landing on Mars is actually harder than landing on the moon. The moon has no atmosphere worth speaking of. That means no air resistance, no weather, and no surprises. You fire your engines, slow down, and touch down. It's dangerous, yes, but straightforward in its own stark way. Mars, on the other hand, has just enough atmosphere to cause trouble, but not enough to be helpful. It's too thin to rely on parachutes alone, and too thick to ignore. Spacecraft entering the Martian atmosphere hit it at incredible speeds, heating up rapidly, while still needing to slow down enough to land gently. Engineers sometimes call this phase 7 minutes of terror, because once it begins, there's nothing anyone on Earth can do to help. Signals take too long to travel. By the time Earth receives confirmation that something went wrong, the outcome has already been decided. For human missions, that risk grows dramatically. A rover can fail, and while disappointing, the mission continues in other ways. A human landing leaves no room for error. Every system must work, not just once, but perfectly, while carrying people who cannot simply be replaced or rebooted. And even if you land safely, Mars is not waiting with open arms. The surface is cold, dry, and exposed to radiation. Mars lost most of its magnetic field billions of years ago, which means it no longer has strong protection from cosmic rays and solar radiation. On Earth, our magnetic field and thick atmosphere act like a shield, quietly absorbing and deflecting much of this invisible danger. On Mars, that shield is thin and patchy at best. Living on the moon would expose astronauts to radiation too, but for much shorter periods. A few days, maybe a couple of weeks. On Mars, exposure would last for years. The journey there, the stay on the surface, and the journey back all add up. Radiation doesn't announce itself loudly. It works slowly, increasing cancer risk, damaging cells, and affecting the nervous system in ways we are still trying to fully understand. This means that going to Mars isn't just about getting there. It's about what happens to the human body over long stretches of time in an environment it was never designed for. Muscles weaken, bones lose density, fluids shift in strange ways, even eyesight can change. These effects begin to show up after months in space, not years, and Mars missions demand both. Then there's the question of supplies. On the Moon, missions could rely heavily on Earth. Equipment was pre-positioned, timelines were tight. If something ran low, the mission was probably already close to ending. Mars does not allow for that kind of dependency. Everything needed to survive must either be brought along or produced on site: air, water, food, fuel. Every kilogram adds cost and complexity. This is why modern Mars planning focuses so heavily on learning how to use local resources. Can we extract water from Martian soil? Can we produce oxygen from carbon dioxide? Can we grow food in controlled habitats? These are not luxuries, they are requirements. Without them, a Mars mission is not sustainable. When people ask why we haven't gone to Mars yet, the honest answer is not that we lack ambition. It's that Mars demands a level of preparation and self-sufficiency we are still learning how to achieve, and all of this unfolds far from Earth, with communication delays that make real-time conversation impossible. A message sent from Mars can take anywhere from 4 to 24 minutes to reach Earth, depending on where the planets are in their orbits. That means no immediate advice from mission control, no quick reassurance, no back-and-forth troubleshooting. Crews on Mars must be capable of handling emergencies on their own, calmly and correctly, with no outside help. That changes who can go, how they are trained, and how missions are designed. Astronauts become explorers, engineers, doctors, and problem solvers all at once, operating in isolation for years. So when we say the Moon was a small step, and Mars is a much longer journey, we're not just talking about kilometers, we're talking about responsibility, about time, about what it means to leave Earth not knowing when, or if, you'll be able to return quickly. The Moon allowed us to practice leaving home while still keeping one foot in the doorway. Mars asks us to close the door behind us, at least for a while, and trust that we've packed everything we need. And as we continue this exploration together, gently and without hurry, we'll keep pulling on these threads: distance, time, risk, human limits. Each one adds weight to the question of why Mars is so much harder, even though we've already proven that reaching beyond Earth is possible. For now, it's enough to sit with that contrast. A world 3 days away versus a world that takes months to reach. A journey with a safety net versus one that demands commitment from the moment you leave. Long before the Moon became a destination with coordinates, checklists, and mission patches, it existed in a very different category of the human imagination. It was not a place you planned to visit. It was something you looked at, something distant, untouchable, quietly present above every civilization that ever existed. For most of human history, the idea of going there was not ambitious or unrealistic. It was simply unthinkable. If you rewind far enough, before rockets and radio waves, before the language of orbits and fuel ratios, the Moon belonged entirely to stories. It governed calendars and tides, marked the passage of months, and shaped rituals that had nothing to do with technology. People tracked it carefully, even obsessively, but never with the assumption that one day a human footprint might press into its surface. The Moon was reliable, predictable, and unreachable all at once. That combination gave it power. Even when early scientists began to understand that the Moon was a physical object, a world rather than a light, it did not suddenly become attainable. Knowing what something is does not automatically make it accessible. For centuries, the gap between Earth and the Moon felt absolute. There was no gradual sense that humans were inching closer, no stepping stones, no intermediate practice runs. The Moon sat beyond the sky in a way that felt final. What's easy to forget now is that this sense of impossibility lingered far longer than we might expect. As recently as the early 20th century, the Moon was still considered unreachable by serious scientists. Writers could imagine trips there in fiction, usually involving cannons, balloons, or strange imaginary forces, but engineers and physicists treated those stories as entertainment, not blueprints. Gravity was well understood by then. Escape velocity was known, and the conclusion was simple. Nothing humans could build could lift itself fast enough, high enough, or long enough to leave Earth behind. That perception began to crack only when two developments collided. One was theoretical, the other was deeply political. On the theoretical side, rocketry slowly transformed from speculation into something measurable. Mathematicians and engineers began to show, on paper at least, that a rocket could work in the vacuum of space, that it did not need air to push against, and that momentum alone could carry it forward. These ideas were not immediately embraced. They sounded counterintuitive and impractical, but they were correct. The second development had nothing to do with curiosity or exploration. It was driven by fear. During the mid-20th century, as global tensions escalated, rockets stopped being abstract ideas and became weapons. The same principles that could, in theory, lift something toward the moon could also deliver payloads across continents. Governments poured money into missile development not because they wanted to explore space, but because they wanted leverage, control, deterrence. Out of that environment, spaceflight emerged almost accidentally. By the time the first artificial satellites were launched, the moon had shifted categories. It was no longer unreachable in principle, it was unreachable in practice, which is a very different thing. Once something is theoretically possible, it begins to exert pressure. It becomes a challenge rather than a fantasy. Still, even in the early days of space exploration, the moon was not an obvious goal. Reaching orbit around Earth was difficult enough. Keeping a human alive outside the atmosphere for minutes, then hours, then days, required solving problems no one had ever encountered before. Weightlessness affected the body in unexpected ways. Radiation levels were poorly understood. Navigation beyond Earth relied on calculations that left little room for error. The first humans in space were not pioneers in the romantic sense. They were test subjects. Their missions were short by necessity, and every second was closely monitored. If something went wrong, there was no backup plan beyond hoping the capsule survived re-entry. Against that backdrop, the moon still felt distant, even as rockets improved. Then politics intervened again. The decision to go to the moon was not born out of a calm, methodical evaluation of scientific priorities. It was a response to competition.
One side had demonstrated early success in space, and the other needed a goal that was dramatic, visible, and difficult to match quickly. Orbit was no longer enough. Staying in space longer was incremental. The moon, on the other hand, was unmistakable. You could not fake it. You could not partially achieve it. Either you went there or you did not. What followed was one of the most concentrated bursts of technological development in human history. To modern eyes, the pace can feel unreal. In less than a decade, humans went from barely reaching orbit to landing on another world. This was not because the moon suddenly became easy. It was because nearly unlimited resources were directed toward a single outcome. Budgets expanded rapidly. Entire industries reorganized. Failure was tolerated only if it led to rapid improvement. It's important to pause on that point, because it often gets blurred in hindsight. The moon landings were not the result of slow organic progress. They were the result of urgency. Deadlines were fixed publicly. Timelines were compressed aggressively. Risks were accepted that would never be approved today. Every part of the mission carried unknowns. Engineers were building systems that had no precedent. Computers were primitive, yet tasked with navigation tasks that demanded precision. Astronauts trained for scenarios that no human had experienced, practicing responses to failures that no one fully understood.
The moon was not welcoming during this process. It did not reveal itself gradually. Each mission uncovered new problems. Temperatures swung wildly, dust behaved unpredictably, communication glitches appeared, mechanical systems failed in ways simulations had not predicted. And yet, step by step, the path forward emerged. One of the most underappreciated aspects of the moon missions was how constrained they were by time. Not just mission duration, but political time. The effort had a window. It was never meant to be permanent. The goal was not to establish a sustained presence, but to arrive, demonstrate capability and return. That shaped everything. Spacecraft were designed for short-term survival, not long-term comfort. Redundancy existed, but it was limited by weight. Life support systems were not built to operate indefinitely. Astronauts carried just enough to complete the mission, with margins that would be unacceptable for longer journeys. The Moon, in other words, was treated as an extreme but brief exposure. This framing matters because it allowed risks to be contained. A few days of radiation exposure was acceptable. A few days of isolation was manageable. A few days of reliance on complex systems felt survivable. Mars does not fit into that framework. But before getting there, it's worth appreciating just how bold the Moon effort was at the time. The Moon felt impossible until it suddenly became urgent. And urgency has a way of bending perceptions. Publicly, confidence was emphasized. Speeches framed the goal as challenging but achievable. Behind the scenes, uncertainty dominated. Failure was a real possibility at every stage. Several missions came close to disaster. Others ended tragically before ever leaving Earth. What carried the effort forward was not certainty, but momentum. Each success narrowed the unknowns. Each failure refined understanding. Slowly, the Moon transitioned from an abstract symbol to a physical destination with known parameters. Distances were measured accurately. Trajectories were refined. Surface conditions were mapped. The Moon became familiar. That familiarity is what makes it feel deceptively easy in retrospect. We tend to compress history. We look back at the Moon landings and see a straight line from decision to success. In reality, it was a jagged path, full of improvisation and recalibration. The Moon did not yield because it was simple. It yielded because it was close enough, and because the effort to reach it was sustained intensely, albeit briefly. Once that intensity faded, so did the momentum. After the final lunar missions, priorities shifted. Budgets tightened. Public attention moved on. Space exploration did not stop, but its character changed. Long-term projects replaced sprint-like efforts. Risk tolerance decreased. Incremental progress became the norm. And the Moon, having been reached, lost some of its symbolic power. It was no longer the impossible dream. It was the accomplished one. This is where the comparison with Mars often begins to break down. Mars did not inherit the same urgency. It did not arrive at the centre of global attention as part of a singular political moment. Instead, it remained a long-term aspiration, revisited repeatedly but never pursued with the same concentrated force. That doesn't mean Mars is less important. It means it exists in a different category of ambition. When the Moon was impossible, it was also immediate. It loomed close enough to feel tangible. You could point to it. You could see it from anywhere. That visibility mattered. It made the goal concrete. Mars does not have that advantage. It is visible only at certain times, faint and distant even then. It does not dominate the night sky. It does not feel present in daily life. As a result, it does not exert the same psychological pull. And yet, in many ways, Mars today occupies the same conceptual space the Moon once did. It is the next unreachable place. The one that sits just beyond our current capability, close enough to imagine, far enough to resist. The difference is that we now understand much more about what that resistance entails. When the Moon was the impossible dream, many challenges were unknown. That ignorance made boldness easier. Mars is harder in part because it is better understood. Every problem is visible in advance. Every risk can be quantified, at least partially, and knowing what can go wrong makes caution rational. This contrast will keep resurfacing. The Moon as a challenge that could be compressed into a moment. Mars as a commitment that stretches across years. The Moon as a proof of concept. Mars as a test of endurance. It's enough to sit with the idea that the Moon was not always a stepping stone. It was once the edge of possibility itself. Reaching it required a specific alignment of knowledge, resources, urgency, and willingness to accept risk. Mars asks for those things too, but in a very different configuration. There is a way people sometimes talk about the Moon that makes it sound almost neighbourly, as if it sits just outside Earth's fence line, close enough to wave at. That phrasing might feel casual, even dismissive, but there is a quiet truth hiding inside it. On the scale of the universe, the Moon really is close, remarkably close. So close, in fact, that this proximity shaped nearly every decision that made human lunar travel possible in the first place. To appreciate that closeness, it helps to strip away the romance for a moment and look at the numbers, gently and without intimidation. The Moon is, on average, about 384,000 kilometers away from Earth. That sounds enormous, and in everyday terms it certainly is, but in spaceflight terms, it is a manageable distance. Light takes just over a second to travel from Earth to the Moon. A radio signal does the same. That means when astronauts spoke from the lunar surface, the delay was noticeable but small. Conversations still felt like conversations. Instructions could be given and adjusted in real time. Questions could be asked and answered before anxiety had time to settle in. This single fact, the near immediacy of communication, quietly lowered the psychological and technical stakes of lunar missions in ways that are easy to overlook today. When something went wrong, and things often did, help was only a breath away. Mission Control could hear a problem as it unfolded. Engineers could walk astronauts through procedures step by step. Decisions could be shared rather than shouldered alone. Even silence had meaning. If communication cut out, it was alarming, but not hopeless. The Moon was close enough that systems could often be restored before catastrophe set in. Now imagine the same scenario, but stretch that communication delay to 20 minutes. Imagine asking a question, waiting and waiting, knowing that whatever you are facing must be managed without guidance. That contrast alone explains why the Moon felt like something humans could dare to attempt, while Mars still demands a different mindset entirely. But communication is only one part of what closeness provides. Distance shapes time, and time shapes risk. A journey to the Moon takes about 3 days, not weeks, not months. 3 days from launch to arrival. That brevity meant that many dangers were naturally limited. Astronauts were exposed to radiation for a short period. Life support systems only needed to function for a tightly bounded window. Food, water, and oxygen could be carried with reasonable margins. Even human endurance, both physical and mental, was tested only briefly. Short journeys compress uncertainty. If a spacecraft developed a problem halfway to the Moon, it was already closer to home than to launch. Turning around was always an option. The trajectory itself allowed for abort paths, carefully designed routes that could loop a spacecraft back to Earth if something failed. These so-called free return trajectories were not conveniences. They were lifelines. They meant that even without engine burns, gravity could guide astronauts home. That safety net was only possible because the Moon is nearby, and because Earth's gravitational influence remains strong across that distance. Mars does not offer this kind of reassurance, but we'll come back to that later. For now, it's important to linger on how much confidence this proximity quietly provided. The Moon's closeness also made testing and iteration possible. Early missions could be planned, launched, evaluated, and followed up relatively quickly. Engineers did not have to wait years to learn whether a design worked. Feedback cycles were short, problems revealed themselves, were studied, and could be corrected on the next mission. That rhythm of attempt, adjustment, and retry is the heartbeat of engineering progress. The Moon allowed it to beat fast. There is also the matter of navigation, which becomes far more forgiving when your destination is nearby. Navigating to the Moon required precision, yes, but it relied on well-understood physics and strong gravitational cues. Earth's pull dominates the journey almost the entire way. The Moon's gravity gently takes over near arrival. The math is complex, but the environment is stable. Mars travel, by contrast, involves cruising through interplanetary space for months, guided by subtle corrections and long stretches where nothing seems to happen at all. Errors accumulate quietly. Tiny miscalculations can grow into massive deviations over time. The Moon does not give mistakes that much room to grow. Even visually, the Moon provided comfort. Astronauts could look back and see Earth, always present, always recognizable. That sight is not just poetic, it matters psychologically. Earth in the window is a reminder of orientation, of belonging, of return. It anchors the mind. On the way to Mars, that anchor eventually disappears. Earth shrinks into a pale dot, indistinguishable from the background. That moment when home stops being a place and becomes a point of light carries weight. The Moon never forced astronauts to cross that threshold. Then there is gravity itself. The Moon's gravity is about 1/6 of Earth's. That number often gets mentioned casually, but its implications are profound. Low gravity makes landing easier. It reduces the energy required to slow down. It allows for simpler descent profiles. Once on the surface, it reduces strain on equipment and on the human body. The Moon also lacks a meaningful atmosphere. That might sound like a disadvantage, and in some ways it is, but for landing it simplifies the problem. There is no air resistance to fight unpredictably. No winds, no weather, no erosion. What you calculate is largely what you get. Mars complicates every one of these factors, but again, patience. We're still on the sidewalk looking across the street, because what truly makes the Moon feel close is not just physical distance, but predictability. The Moon is tidally locked to Earth, meaning it always shows the same face. Its orbit is stable and well characterized. Its environment changes slowly. Once you understand it, it does not surprise you often. That reliability is a gift to mission planners. Mars is dynamic. Its distance changes constantly. Its seasons are long and uneven. Its atmosphere, thin as it is, still produces storms that can cover the entire planet. Dust behaves in ways that challenge machinery and visibility. The Moon simply sits there, quiet and consistent. This predictability allowed the Moon to become a proving ground, not just for rockets and landers, but for procedures, training, and human behavior in space. Astronauts learned how their bodies reacted to weightlessness. They learned how tools behaved in vacuum. They learned how fatigue set in, how mistakes crept in, how teamwork held up under pressure. All of this knowledge came from missions that were short enough to survive and close enough to monitor. From a planning perspective, the Moon offered clarity. Every mission had a defined beginning, middle, and end. Supplies were counted carefully. Schedules were tight. There was no ambiguity about duration. You went, you worked, you came home. Mars blurs those boundaries. But staying with the Moon a bit longer, there is another subtle advantage that often goes unmentioned. The Moon's closeness allowed public engagement to remain high. People watched launches knowing the outcome would be known soon. The feedback loop between effort and reward was short. That matters for sustained support. A Mars mission asks the public to wait years between launch and meaningful milestones. That kind of patience is harder to maintain, especially across changing political landscapes and shifting priorities. The Moon benefited from immediacy in every sense. Even failure was immediate. When missions failed, the reasons became clear quickly. Lessons could be drawn while teams were still intact and focused. There was momentum, a sense that progress was continuous. This is not nostalgia, it is logistics. When people today ask why we don't simply repeat the Moon landings and extend them outward to Mars, they're often assuming that space is a uniform medium, like water or air, where distance only changes scale, not character. In reality, space changes with distance. Time stretches. Communication frays. Margins evaporate. The Moon sat within a comfortable radius of control. It allowed Earth to remain involved at every step. It allowed humans to dip a toe into deep space without fully committing to it. It allowed mistakes to be serious without being fatal by default. And perhaps most importantly, it allowed confidence to grow faster than fear. Mars does not offer that luxury. As we move away from Earth, we don't just move through space, we move away from rescue, away from oversight, away from immediacy. The Moon never forced us to confront that fully. It let us practice, briefly and intensely, before returning us to safety. That is why calling the Moon just across the cosmic street is not an insult to the achievement. It is an explanation of how it was possible. You can cross a street quickly. You can run back if something goes wrong. You can shout to someone on the other side and be heard. You can see where you're going clearly. Mars is not across the street. It is across town, across the desert, across a stretch of road with no exits and no shortcuts. Understanding that difference is essential, because without it, the question of why Mars is harder sounds like a failure of will or imagination. In reality, it is a reflection of geometry, physics, and human limits interacting in ways that no amount of optimism can erase. The Moon did not make us interplanetary. It showed us how fragile we are when we leave Earth, even for a few days. It taught us that distance is not just a number, but a multiplier. Multiply time, multiply risk, multiply responsibility. At first glance, Mars seems like it should behave the way neighbours usually do. It's nearby. It shows up regularly in the night sky. Sometimes it even shines brightly enough to catch your eye without trying. Compared to the vast emptiness beyond, Mars feels approachable, almost familiar. And yet, when you start planning an actual journey there, it develops a frustrating habit. Just when you think you're getting close, it drifts farther away. This is one of the most quietly important reasons Mars is so much harder to reach than the Moon. Not because it is always far, but because it refuses to stay put. Earth and Mars are both moving. That may sound obvious, but the consequences of that shared motion are anything but simple. Each planet follows its own orbit around the Sun, at its own speed, along its own path. Earth moves faster on an inner track. Mars moves more slowly on a wider one. Sometimes Earth catches up, sometimes it pulls ahead, sometimes the two are on the same side of the Sun, and sometimes they are separated by its full width, hidden from each other by a wall of blazing light. This constant motion means there is no fixed distance to Mars, there is only a changing relationship. At their closest, Earth and Mars can be about 56 million kilometers apart. At their farthest, that distance can stretch to more than 400 million kilometers. That's a difference of over 7 times. Imagine trying to plan a road trip where your destination sometimes moves 7 times farther away depending on the day you leave. The challenge is not just distance, it is timing. For the Moon, timing barely matters. Its orbit around Earth is regular and short. You can launch toward it on almost any given day and expect roughly the same journey. Mars does not allow that flexibility. To travel efficiently, spacecraft must leave Earth during specific windows when the planets are aligned in a way that minimizes fuel use and travel time. These windows are not rare by cosmic standards, but they are infrequent by human ones. Roughly every 26 months, Earth and Mars settle into a configuration that opens the door. Miss that door, and it closes firmly. This has immediate consequences. Missions must be planned years in advance, with little room for delay. Hardware must be ready. Crews must be trained. Funding must be secured. Political support must hold. And all of that must converge on a launch date that is not negotiable. If something slips, there is no simple postponement of a few weeks. The next opportunity may be more than 2 years away. That rigidity alone adds pressure to every Mars mission in a way lunar missions never experienced. But the moving target problem does not stop at launch. Once a spacecraft leaves Earth, Mars continues to move. The spacecraft does not fly straight toward where Mars is now, but toward where Mars will be months later. This requires precise calculations and confidence that nothing significant will change during the long cruise. Corrections are possible, but they cost fuel. Fuel is weight is expense, and expense is limitation. On a trip to the Moon, navigation adjustments happen over hours. On a trip to Mars, they unfold over weeks and months. Tiny errors that would be trivial on a short journey become consequential over time. The longer you travel, the more opportunity there is for small uncertainties to grow. Then there is the matter of speed. To reach Mars efficiently, spacecraft follow curved paths known as transfer orbits. These paths are not chosen for comfort or directness. They are chosen because they save energy. Instead of pointing at Mars and firing engines continuously, spacecraft coast along a carefully shaped arc, falling toward the Sun in a way that intersects Mars's future position. This means the journey is slow by design. Typical travel times to Mars range from 6 to 9 months. During that entire period, the spacecraft is not heading toward Mars in any intuitive sense. It is drifting, adjusting, waiting. Mars slowly grows from a faint dot into a recognizable disk. Earth slowly fades behind. That long wait introduces challenges that simply do not exist on shorter trips. Supplies must last. Systems must operate reliably for months without maintenance. Any failure must be managed with limited tools and limited options. There is no nearby destination to divert to. There is no quick return path. The moving target has already moved on, and this is where Mars truly earns its reputation as a difficult neighbour. If you imagine Earth and Mars as runners on a track, Earth sprints ahead on the inside lane while Mars jogs steadily farther out. To meet Mars, Earth has to slow down, time its pace, and arrive at a precise point at a precise moment. Arrive too early, and Mars is not there yet. Arrive too late, and it has already passed. The Moon does not play this game. It stays close. It stays in sync. Mars also complicates the return journey in ways that are easy to underestimate. You cannot simply turn around and head back whenever you want. Once you arrive at Mars, you're committed to staying until the planets line up again in a favourable way. That waiting period can last more than a year. This means a Mars mission is not a round trip in the usual sense. It is 2 one-way journeys connected by a long stay in between. You go when the window opens. You return when the window opens again. Everything else must be built around that schedule. That requirement alone reshapes mission design completely. On the Moon, astronauts could stay a few hours or a few days and leave when they were ready. On Mars, staying is mandatory. Even if everything goes perfectly, there is no option to shorten the mission significantly. You arrive, you live there, and you wait. Living on a moving planet, orbiting far from Earth, introduces another layer of complexity. Mars's orbit is more elliptical than Earth's, meaning its distance from the Sun varies more dramatically over time. This affects temperature, solar energy availability, and atmospheric behaviour. Seasons on Mars are longer and more extreme. Dust storms can emerge and persist for weeks or months, reducing sunlight and coating everything with fine particles. These environmental changes are tied directly to Mars's motion around the Sun. You cannot choose to arrive during a calm period and leave before conditions worsen. You arrive when the window allows, and you deal with whatever Mars is experiencing at that moment in its long year. Communication adds its own moving target complications. As Earth and Mars orbit the Sun, the distance between them changes constantly. Sometimes signals take just a few minutes to travel. Sometimes they take nearly half an hour one way. During certain alignments, the Sun itself sits between Earth and Mars, blocking direct communication entirely for weeks at a time. During these solar conjunctions, Mars crews would be completely on their own. No real-time updates, no immediate advice, only pre-planned messages and onboard autonomy. This is not a flaw in technology, it is a feature of geometry. Mars's refusal to stay close also affects rescue scenarios, or more accurately, the lack of them. On the Moon, rescue missions were theoretically possible, difficult, dangerous, and unlikely, but not impossible. Another spacecraft could be launched within days, trajectories could be adjusted, help could arrive while it still mattered. On Mars, rescue is not a realistic concept. If something goes catastrophically wrong, There is no outside intervention that can reach the crew in time. Survival depends entirely on preparation, redundancy, and the ability to solve problems without outside assistance. That reality changes the psychology of the mission. It changes who can go. It changes how systems are designed. It changes how risk is evaluated. When Mars moves away, it takes Earth's safety net with it. This is not a matter of bravery or determination. It is a structural constraint imposed by orbital mechanics. No amount of courage can shorten the distance or slow the planets. Mars operates on its own schedule, indifferent to human ambition. Even robotic missions feel this constraint. Rovers and landers must operate autonomously because commands arrive too late to be useful in real time. They plan their days carefully, conserving energy, avoiding hazards, and waiting patiently for instructions that arrive long after the environment has changed. Humans on Mars would face the same reality, but with higher stakes. Every decision would carry consequences that unfold slowly and cannot be easily undone. Mistakes cannot be corrected quickly. Success depends on foresight rather than reaction. This is why Mars exploration has progressed cautiously, not because we lack the ability to build rockets, but because we are learning how to operate responsibly at a distance where help does not arrive on time. There is also a subtle emotional aspect to Mars's moving nature. The moon feels present. You can step outside and see it. It reminds you of the journey you took and the one you can take again. Mars is intermittent. It appears, brightens, fades, and disappears. Out of sight for long stretches, it slips from public consciousness. This makes sustained attention difficult. Missions must survive long periods without visible reinforcement. Years pass between launches. Decades pass between major milestones. Momentum is harder to maintain when the target keeps drifting out of view. And yet this same quality is part of what makes Mars compelling. It resists us not by being unreachable, but by being patient. It forces us to match its rhythm rather than impose our own. It demands planning on planetary timescales rather than political ones. Understanding Mars as the neighbour that moves away reframes the question of difficulty. It is not that Mars is farther in a simple sense. It is that Mars does not cooperate. It does not align itself for our convenience. It does not wait. To go to Mars, we must wait for it. The moon allowed us to act quickly and return quickly. Mars stretches every action across months and years. It replaces urgency with patience and reaction with anticipation. Distance is a strange thing. On a map it looks clean and manageable. A line stretches from one point to another, a number is written beside it, and the mind quietly files the information away as solved. But in space, distance behaves less like a measurement and more like a pressure. It pushes on every system, every decision, every assumption. And the farther you go, the more that pressure tightens. When people talk about Mars being far away, they often mean it casually, the way you might describe a long drive or a distant country. But distance in space is not experienced the way distance on Earth is. There are no rest stops, no alternate routes, no quick detours. Once you leave, distance becomes something you live inside. This is the tyranny of distance, and it is one of the most unforgiving reasons Mars is so much harder than the Moon. To begin with, distance controls time, and time controls exposure. A trip to the Moon takes days. A trip to Mars takes months. That single difference multiplies risk in ways that compound quietly. Radiation exposure does not arrive all at once. It accumulates. Every extra day outside Earth's protective magnetic field adds to the total dose absorbed by the human body. Over a lunar mission, that exposure is limited. Over a Mars mission, it becomes a defining concern. Earth is wrapped in a magnetic field that deflects much of the high-energy radiation streaming through space. Low Earth orbit still benefits from this shield. Even the Moon, though outside it, is close enough that astronauts pass through regions of partial protection during their journey. Mars travel offers no such relief. Once you leave Earth, You're exposed continuously for months on end. Radiation is invisible, silent, and cumulative. It damages DNA, increases cancer risk, and affects the nervous system in ways that are still being studied. Shielding helps, but shielding is heavy. Heavy requires more fuel. More fuel increases launch mass. Launch mass increases cost and complexity. Distance turns every protective measure into a trade-off. Then there is the matter of supplies. On Earth, distance can be overcome by resupply. If something runs low, more can be sent. Even the International Space Station depends on this logic. Regular cargo missions replenish food, water, air, spare parts, and experiments. The station can function long-term because Earth is nearby. The Moon, again, sits close enough that resupply is difficult but conceivable. Mars does not allow it. Once a crew departs for Mars, what they have is what they have. There is no mid-mission delivery, no emergency shipment, no forgotten wrench arriving next week. That reality changes how missions are designed at a fundamental level. Every kilogram must justify its presence. Redundancy becomes essential, but redundancy adds mass. Spare parts must cover failures that may not occur for years. Systems must be repairable by the crew themselves, with limited tools and no expert assistance. Distance forces self-reliance. This extends to food in ways that are often underestimated. For short missions, pre-packaged food works well. For long missions, it becomes monotonous, bulky, and nutritionally limiting. Mars missions must consider food production, not just storage. Growing food reduces reliance on shipped supplies, but it introduces new systems that can fail. Lighting, water circulation, nutrient balance, and microbial control all become mission critical. On the Moon, astronauts could tolerate inconvenience. On Mars, inconvenience compounds into risk. Distance also erodes communication in ways that go beyond simple delay. When signals take minutes to travel one way, conversation stops being interactive. Dialogue becomes correspondence. You send information. You wait. You receive a response based on a past situation. By the time advice arrives, conditions may have changed. This delay forces crews to operate independently. They must diagnose problems, choose solutions, and act without confirmation. That autonomy is empowering in theory, but stressful in practice. Knowing that help exists but cannot reach you in time creates a unique psychological burden. Over long durations, that burden matters. Isolation deepens with distance. A lunar crew knows they are days from home. A Mars crew knows they are months away, even if everything goes perfectly. That awareness is not abstract. It shapes mood, decision-making, and resilience. Small tensions have more time to grow. Conflicts cannot be escaped. Privacy is limited. Routine becomes rigid. Distance traps you with your environment and with each other. Even sleep changes. Light cycles shift. Mars days are slightly longer than Earth's. Over time, that difference affects circadian rhythms. Fatigue accumulates subtly. Attention drifts. Errors become more likely. These are not dramatic failures. They are slow degradations, exactly the kind distance encourages. The tyranny of distance also manifests in maintenance. On Earth, machines fail and are repaired. In orbit, machines fail and are repaired. On Mars, machines must fail gracefully. Systems must be designed to degrade without collapsing. A broken pump cannot mean the end of air circulation. A cracked seal cannot mean habitat loss. Every component must assume it will be stressed for years. Distance also limits testing. Lunar hardware could be tested in short missions and refined quickly. Mars hardware may not reveal its flaws until long after launch. By then, replacement is impossible. That reality forces extreme conservatism in design, slowing progress and increasing cost. Then there is the question of return. A Mars mission is not simply about reaching Mars, it is about surviving long enough to come back. Distance dictates that return fuel must either be carried or produced on Mars. Carrying it increases launch mass dramatically. Producing it requires reliable chemical processes operating in an alien environment. Distance turns return into a problem as complex as departure. On the Moon, ascent was comparatively straightforward. Low gravity and proximity to Earth simplified calculations. Mars complicates ascent with its gravity and atmosphere. Launching from Mars requires more energy than leaving the Moon, and that energy must come from systems that have been sitting idle, exposed to dust and cold for months. Distance ensures there is no rehearsal. Even emergencies take on a different character. A medical issue on the Moon could prompt an early return. On Mars, there is no early return. Medical systems must handle issues ranging from minor injuries to serious illness without evacuation. Crew selection becomes critical. Training must be extensive. Psychological resilience matters as much as physical health. Distance forces preparation to replace improvisation. There is also a subtle but important effect on mission timelines. Mars missions cannot be shortened easily. The physics of orbits dictates minimum durations. That inflexibility means crews cannot choose to cut things short. If conditions deteriorate, they must endure. This endurance requirement changes how risk is evaluated. Acceptable risk on a 3-day mission is not acceptable on a 3-year mission. Small probabilities add up over time. A 1% chance per month becomes significant over years. Distance amplifies probability. Public perception is shaped by this too, whether consciously or not. The Moon felt like a bold leap, but one with a visible arc. Mars feels like a slow drift into uncertainty. The rewards are distant. The risks are prolonged. That asymmetry makes support fragile. Distance does not inspire excitement the way spectacle does. It inspires caution. And yet, distance is not merely an obstacle. It is also a teacher. It forces clarity. It demands systems that can endure. It exposes weaknesses early in planning, if not in execution. It reminds us that space is not forgiving. The Moon let us flirt with space. Mars demands a relationship. As distance increases, human control decreases. You cannot micromanage across millions of kilometers. You cannot react instantly. You must trust design, training, and judgment. That trust must be earned, not assumed. This is why Mars exploration has leaned so heavily on robots. Machines tolerate distance better than humans. They do not suffer loneliness. They do not accumulate radiation-induced anxiety. They can wait patiently for instructions. Even so, they fail, often in ways that reveal just how harsh Mars can be. Each robotic mission teaches lessons about distance, delays, dust, wear, degradation. These lessons accumulate slowly, shaping future plans. The tyranny of distance is not dramatic. It does not announce itself with explosions or alarms. It works quietly, steadily, making everything harder, heavier, slower, and more complex. When we compare the Moon and Mars, it is tempting to focus on singular challenges: atmosphere, gravity, radiation. But distance ties them all together. It is the background condition that magnifies every other problem. On the Moon, distance allowed us to be bold. On Mars, distance demands humility. Mars is not simply farther away, it is farther away for longer. And that distinction changes everything, quietly but completely, as the journey stretches on and the space between home and destination grows not just larger, but heavier, shaping every moment that unfolds along the way. One of the quiet comforts of the Moon missions, even when everything felt risky, was the knowledge that leaving was always possible. Not easy, not guaranteed, but possible. If something went wrong, there were paths home. They were narrow and demanding, but they existed. That fact alone shaped how astronauts thought, how engineers planned, and how risk was tolerated. Mars removes that comfort almost entirely. When you travel to Mars, You're not buying a round-trip ticket in the ordinary sense. You're committing to a sequence of events that cannot be shortened once it begins. There is no option to turn around after a few days and try again later. There is no realistic scenario where help arrives quickly. You go, you stay, and only much later do you return. That is not drama. It is geometry. To understand why this matters so much, it helps to return briefly to how moon missions were designed. Lunar trajectories were carefully chosen to allow what engineers called abort modes. If the main engine failed on the way out, gravity could still guide the spacecraft back to Earth. If a system malfunctioned after orbiting the moon, astronauts could fire engines and begin the return almost immediately. Even during the descent to the lunar surface, there were points where a landing attempt could be abandoned. This flexibility did not make moon missions safe, but it made them survivable in a wider range of scenarios. It allowed crews and mission control to respond to problems with action rather than resignation. Decisions mattered because they could still change outcomes. Mars does not grant that kind of agency. Once a spacecraft is on its way to Mars, turning back is not a simple reversal. The energy required to cancel the trajectory and return to Earth is enormous, far beyond what a Mars-bound vehicle is designed to carry. Fuel margins are tight by necessity. Every kilogram of propellant competes with food, water, air, and equipment. There is no extra tank labeled just in case. Even if fuel were available, the timing would rarely work in your favour. Earth would not be where you left it. You would be chasing a moving planet from behind, fighting orbital mechanics rather than working with them. The math does not support impulsive decisions. This means that a Mars crew must accept before launch that once they depart Earth, they are not coming back for a long time. Not because something might go wrong, but because even if everything goes right, that is simply how the journey works. That psychological commitment is enormous. Imagine knowing, with certainty, that for the next 2 to 3 years, your options are fixed. You cannot shorten the trip. You cannot speed up the return. You cannot call it off. You're stepping into a process that will unfold on its own schedule, indifferent to discomfort, boredom, fear, or doubt. This is not how humans are accustomed to travel. Even the longest journeys on Earth carry the possibility of interruption. Flights can land early, ships can turn back, roads offer exits. Mars offers none of that. Once you're on the interplanetary path, you're following it whether you feel ready or not. The absence of a quick return option changes how risk is evaluated at every stage. For lunar missions, engineers could accept certain hazards, knowing that exposure time was short. A radiation spike might be dangerous, but brief. A system anomaly might be tolerated if it could be managed until return. On Mars, time stretches those same hazards into something far more serious. A minor issue that would be acceptable for a week becomes unacceptable over years. This is why Mars missions demand levels of redundancy that seem excessive at first glance. Multiple backups for critical systems, overlapping life support functions, spare parts for failures that may never occur, training that assumes isolation rather than support. Every layer exists because once you are there, you cannot leave. Medical planning illustrates this starkly. On the Moon, astronauts accepted the risk of injury knowing that evacuation was possible. A Mars crew does not have that option. Medical systems must be capable of handling emergencies autonomously. Crew members must be trained to treat conditions they may never have encountered. Equipment must function without resupply. This is not pessimism, it is realism. The same logic applies to mental health. Stress is manageable when there is an endpoint you can see approaching. It becomes heavier when that endpoint is abstract and distant. The knowledge that you cannot simply go home if things become difficult adds a subtle pressure that never fully lifts. This pressure does not need to become panic to be damaging. It works slowly, influencing sleep, mood, and judgment. Over time, small strains can accumulate into serious issues. Mars missions must account for this not by hoping astronauts are immune, but by designing environments, routines, and support structures that acknowledge the weight of commitment. Even communication reflects the lack of a return option. When a problem arises on the Moon, advice arrives almost instantly. When a problem arises on Mars, advice arrives after the problem has already been lived with for a while. Crews must act first and explain later. That reversal of support can feel isolating. Knowing that Earth is listening but cannot intervene creates a unique kind of loneliness. The lack of a quick return also reshapes public responsibility. Sending people to Mars is not just an engineering challenge, it is a moral one. When a society commits to such a mission, it accepts responsibility for the full duration of that commitment. There is no partial fulfillment. You cannot cancel halfway through without severe consequences. This is one reason Mars missions advance slowly. Caution is not hesitation, it is acknowledgement. There is also a practical side that often gets overlooked. A Mars return vehicle must already be waiting on the surface, or its components must be assembled there. You cannot arrive, explore, and then decide how to leave. The exit must be planned before the entry. Fuel must be ready. Systems must be tested. If the return system fails while you're on Mars, there is no alternative. On the Moon, ascent vehicles were carried with the crew. On Mars, carrying everything from Earth becomes prohibitively expensive. This forces reliance on local production, creating another chain of dependency. If fuel production fails, the return fails. If power generation falters, fuel production falters. The return ticket is not just delayed, it disappears. This interdependence magnifies the consequences of failure. Even weather plays a role. Dust storms can reduce solar power for extended periods. If power drops, systems degrade. If systems degrade, return capability is threatened. All of this happens while Earth watches from millions of kilometers away. This is why Mars exploration places such emphasis on proving technologies robotically first. Not because humans are incapable, but because the margin for error is so small. Every unknown must be reduced as much as possible before humans are placed in a situation where leaving is not an option. It is also why timelines feel long and frustrating. Each delay is not just about readiness, it is about responsibility. Once a Mars mission launches, its consequences are locked in. The Moon allowed us to experiment with presence. Mars requires permanence, even if temporary. You must live with your choices for years. There is something quietly sobering about that. Human history is full of journeys that could not be reversed. Migrations, voyages, settlements. But those journeys unfolded on Earth, where resupply, rescue, and adaptation were at least possible. Mars removes those familiar safety nets. That does not make Mars unreachable. It makes it unforgiving. The absence of a quick return ticket does not mean that astronauts would feel trapped every moment. Humans are adaptable. Routine normalizes the extraordinary. Days would still have structure. Work would still fill time. Curiosity would still exist. But beneath all of that would be the constant awareness that there is no exit door. That awareness changes behavior in subtle ways. It encourages caution. It discourages impulsiveness. It demands cooperation. It can strengthen bonds or strain them. Designing missions that acknowledge this psychological reality is as important as designing rockets. This is also why Mars missions tend to emphasize international cooperation. Sharing responsibility spreads risk, cost, and accountability. It reflects the understanding that no single nation can easily shoulder the burden of a journey that cannot be quickly undone. Mars does not allow for bravado. It demands planning that extends beyond enthusiasm. When people ask why we don't simply send humans to Mars now, this is often what they are missing. It is not that we doubt our ability to reach Mars, it is that reaching Mars commits us to seeing the journey through, regardless of complications. The Moon let us dip our toes into deep space and retreat when necessary. Mars asks us to step fully into it and stay there until physics allows us to leave. Mars does not offer second chances in the way the Moon did, and as this idea settles in, it begins to shift how the entire question looks. Mars is not just farther, it is more final, more binding, more patient than we are accustomed to being. The journey outward may feel slow and quiet, but once it begins, it carries everyone involved along a path that cannot be exited early, unfolding steadily toward challenges that must be met not with urgency, but with endurance, foresight, and the steady acceptance that some journeys, once started, simply have to be lived all the way through. Landing sounds like a single moment, a brief punctuation mark at the end of a journey. Wheels touch down, dust settles, you arrive. But in spaceflight, landing is not a moment. It is a long, tightly connected chain of events where fuel, gravity, speed and timing all argue with each other, and where losing control for even a few seconds can undo years of planning. When it comes to Mars, this chain is especially unforgiving. The Moon and Mars may both be rocky worlds, but they ask radically different questions of anything that tries to land on them. The Moon asks one primary thing: can you slow down enough, with enough precision, to meet its surface gently? Mars asks something far more complicated. Can you slow down just enough, in the presence of a thin, unpredictable atmosphere and stronger gravity, without slowing down too much or too little, and do it all while being unable to correct mistakes from Earth? Fuel sits at the centre of this problem, quietly dictating what is possible and what is not. Every space mission begins and ends with fuel budgets. Fuel determines how much mass you can lift, how much speed you can change, and how many mistakes you can afford. On Earth, gravity is strong, but rockets fight it for only a few minutes before reaching orbit. Once in space, motion becomes cheaper. Small amounts of fuel can make meaningful adjustments. The Moon benefits enormously from this logic. Because the Moon's gravity is weak, only about 1/6 of Earth's, landing there requires relatively modest fuel compared to large worlds. There is no atmosphere to complicate the descent. Spacecraft approach the Moon, fire engines to slow down, and descend directly. The math is demanding, but the environment is simple. Gravity pulls downward, engines push upward. There are no winds, no drag, no sudden surprises. Fuel use on the Moon is predictable. If something looks wrong during descent, engines can fire longer. If the landing site appears unsafe, a hover is possible, at least briefly. Apollo astronauts famously use this capability to avoid boulders and craters, manually guiding their lander to safer ground. That flexibility existed because fuel margins, while tight, allowed for human judgment. Mars removes much of that flexibility. Mars has gravity that is strong enough to matter, about 38% of Earth's, but not strong enough to make descent straightforward. Its atmosphere is thick enough to cause heating and drag, but too thin to provide reliable lift or braking. This awkward middle ground is what makes Mars landing so difficult. As a spacecraft approaches Mars, it is moving incredibly fast, faster than anything humans experience on Earth. To land safely, that speed must be reduced dramatically in a matter of minutes. Fuel alone cannot do this efficiently. Carrying enough fuel to slow down entirely with engines would make the spacecraft far too heavy to launch from Earth. So engineers turn to the atmosphere for help. Heat shields allow spacecraft to plunge into the Martian atmosphere, using friction to shed speed. Parachutes deploy to slow things further. Then, at the very end, engines fire to complete the descent. Each stage depends on the previous one working perfectly. If the heat shield fails, the spacecraft burns up. If the parachute fails, the spacecraft hits the ground too fast. If the engines fail, there is no recovery. This sequence has earned a blunt nickname among engineers: 7 minutes of terror. Once it begins, there is nothing anyone on Earth can do to intervene. Signals take too long to travel. By the time mission control knows whether the landing succeeded or failed, it has already happened. For robotic missions, this is nerve-wracking. For human missions, it is existential. Fuel constraints loom over every second of this process. Engines must have enough propellant to handle variations in atmospheric density, surface elevation, and vehicle mass. Mars's atmosphere changes with seasons and dust levels. Its surface is uneven, with landing sites sitting at different altitudes. A site lower in elevation offers more atmosphere to slow down in, which helps. A higher site offers less margin. Choosing where to land becomes a balance between scientific interest and engineering survivability. Fuel must also be reserved for ascent. Unlike the Moon, where ascent fuel requirements are modest, leaving Mars is expensive in energy terms. Stronger gravity and atmospheric drag mean that getting off Mars requires more fuel than leaving the Moon. That fuel cannot simply be carried along easily. It adds enormous mass. This is why Mars mission planners focus so heavily on producing fuel on Mars itself. Using local resources to create propellant reduces the amount that must be launched from Earth. But that strategy creates another dependency chain. If fuel production systems fail, the crew cannot leave. Landing successfully becomes meaningless if departure is impossible. Fuel, in this sense, is not just about landing. It is about the entire mission architecture. Gravity complicates matters further in ways that are easy to underestimate. Mars's gravity is strong enough to pull a spacecraft down quickly, increasing descent speed, but weak enough that it does not provide the same predictable trajectory control as Earth. This means spacecraft spend more time in a regime where neither gravity nor atmospheric drag dominates cleanly. This in-between zone is difficult to model perfectly. Tiny differences in angle, speed, or atmospheric density can lead to large differences in outcome. Engineers simulate these scenarios endlessly, but reality always introduces variation. On the Moon, gravity behaves cleanly. On Mars, it negotiates. Then there is dust. Martian dust is fine, electrostatically charged and persistent. During descent, dust can obscure sensors, interfere with radar readings, and alter aerodynamic behavior. After landing, it coats equipment, reducing efficiency and increasing wear. For ascent vehicles, dust infiltration can affect seals and mechanisms that must work flawlessly months later. Fuel systems hate dust. Every valve, every pump, every combustion chamber must remain clean. A small particle in the wrong place can cause failure. Designing systems that can sit idle in a dusty environment and still function perfectly later is not trivial. The Moon has dust too, but it behaves differently. Lunar dust is sharp and abrasive, but it does not float in an atmosphere. It settles quickly. Mars's dust stays suspended, driven by winds and storms that can last weeks. Gravity also affects how humans move once they arrive, which loops back into landing considerations. On the Moon, low gravity allows for forgiving impacts. A stumble is less dangerous. Equipment can be maneuvered with relative ease. Mars's gravity is strong enough that falls can injure. Tools weigh more. Structures must support greater loads. This influences habitat design, which in turn affects landing mass. Heavier habitats require larger landers. Larger landers require more fuel. More fuel increases complexity. Everything connects. There is also the issue of precision. Lunar landing sites could be relatively broad. A few kilometers of deviation was acceptable. Mars missions require much tighter targeting. Landing near pre-positioned equipment, fuel plants, or habitats demands accuracy within tens of meters. Achieving that precision through an atmosphere with delayed communication pushes guidance systems to their limits. Autonomous navigation becomes essential. Spacecraft must recognize terrain in real time, avoid hazards, and select safe landing zones without human input. These systems exist, but scaling them to human-rated vehicles increases stakes dramatically. Fuel margins shrink as precision increases. Another often overlooked factor is heat. Entering Mars's atmosphere generates intense heat, but not as intense as Earth re-entry. That sounds helpful, but it actually creates design challenges. Heat shields must withstand prolonged heating rather than brief intense bursts. Materials must balance insulation, mass, and durability. Heat shield failure is catastrophic. Overbuilding heat shields adds mass. Added mass requires more fuel. Fuel requires more launch capability. The cycle repeats. Mars does not allow simple solutions. Even after touchdown, the landing problem is not entirely solved. A spacecraft on Mars must remain upright, stable, and functional in an environment where temperature swings are severe. Cold affects fuel lines. Pressure affects seals. Power systems must come online reliably. Any issue during this transition can compromise the mission before it truly begins. On the Moon, astronauts could exit their lander quickly. On Mars, conditions may require waiting, checking systems, and stabilizing habitats before human activity can begin. That delay increases reliance on life support systems immediately after landing, when stress and uncertainty are highest. Fuel planning must account for contingencies during this phase as well. Engines may need to fire again to adjust orientation or stabilize position. Every kilogram burned is one that cannot be used later. This is why Mars landing is often described as the single most dangerous phase of the mission. Not because it is dramatic, but because it concentrates so many risks into such a short time. Months of travel narrow into minutes of outcome. The Moon allowed humans to practice landing in a relatively controlled environment. Mistakes were survivable, adjustments were possible. Mars compresses complexity into a narrow window where flexibility is minimal. Understanding this helps explain why we have landed so many robots on Mars but have not yet sent humans. Robots can be lighter. They can tolerate higher risk. They do not need return vehicles or habitats. They can accept one-way missions. Humans cannot. Every human Mars landing must succeed not just once but repeatedly. It must work for the first crew and the second and the third. It must become routine enough to be trusted, yet robust enough to survive rare events. Fuel, gravity, and landing are not separate challenges. They are a single intertwined problem that defines the entire mission. Change one parameter and the others shift in response. Mars exposes this interdependence ruthlessly. The Moon was forgiving enough to let us learn as we went. Mars demands that much of the learning happen before we ever arrive. That requirement slows progress, but it also reflects maturity. It acknowledges that exploration is not just about reaching a place, but about doing so in a way that allows people to live there and leave safely. Landing is not an endpoint. It is a commitment that locks in everything that comes after. And on Mars, where fuel margins are thin, gravity is insistent and the ground waits without sympathy, that commitment begins the moment descent starts, carrying the mission onward into challenges that cannot be solved by courage alone, but only by preparation, restraint, and a deep respect for the physics that govern how hard it is to touch down on a world that does not make it easy. Surviving the journey is not a single challenge. It is a collection of quiet, persistent demands that begin the moment a spacecraft leaves Earth and do not ease until long after it arrives at its destination. Unlike launch or landing, which concentrate risk into dramatic intervals, survival stretches risk thinly across time. It works slowly. It tests patience more than reflexes. And for a Mars mission, it may be the most underestimated obstacle of all. On the way to the Moon, survival was a short-term concern. Systems needed to function reliably for days, not months. Human bodies had to tolerate weightlessness briefly. Psychological strain existed, but it was contained by the knowledge that home was close and return was imminent. Mars removes those limits. Survival becomes a long conversation between biology, engineering, and environment, one that unfolds over hundreds of days in a setting that offers no forgiveness. The first and most persistent threat is radiation. Earth is unusually generous in this regard. Its magnetic field wraps the planet in a protective bubble, deflecting much of the high-energy radiation that streams through space. Even low Earth orbit benefits from this shield. Astronauts aboard space stations receive more radiation than people on the ground, but still far less than what exists in deep space. A journey to Mars leaves that protection behind. Once the spacecraft clears Earth's magnetic influence, its occupants are exposed continuously to cosmic rays and solar radiation. These are not the kinds of exposures you feel immediately. They do not burn or sting. They work quietly, damaging cells, breaking DNA strands, and increasing long-term health risks in ways that accumulate day by day. Short lunar missions limited this exposure by design. Mars missions cannot. Shielding helps, but shielding is a compromise. Thick layers of material can block radiation, but they add mass. Added mass increases fuel requirements. Increased fuel requirements raise cost and complexity. Every centimetre of protection must justify itself against everything else the spacecraft needs to carry. Even with shielding, exposure remains significant. There is no known way to fully block high-energy cosmic rays without impractically massive barriers. That means Mars crews will absorb radiation doses far beyond anything experienced in previous human missions. Understanding how much is acceptable and how to mitigate damage remains an active area of research. Radiation is not the only invisible threat. Weightlessness changes the human body in fundamental ways. Muscles weaken, bones lose density, fluids shift toward the head, altering pressure in the eyes and brain. Over time, these changes can affect vision, balance, and coordination. On short missions, these effects are reversible. On long missions, recovery becomes more uncertain. Mars travel requires enduring weightlessness for months before arrival, adapting to partial gravity on the surface, then enduring weightlessness again on the return trip. This sequence has never been tested in humans. We know how bodies respond to each phase individually, but not to the combination. Exercise helps, but exercise is not a cure. Astronauts aboard space stations spend hours each day exercising to slow muscle and bone loss. Even so, changes still occur. On a Mars spacecraft, exercise equipment must be compact, reliable, and durable. If it fails, there is no replacement. Survival also depends on air, water, and food systems that cannot fail. On Earth, these systems are supported by vast infrastructure. In orbit, they are supported by regular resupply. On the Moon, they were supported by short mission durations. On Mars, they must operate continuously, autonomously, and redundantly for years. Air must be recycled, carbon dioxide removed, oxygen replenished, water must be purified repeatedly, waste must be processed safely. Any imbalance can become dangerous over time. These are not dramatic failures, they are gradual ones. A slightly inefficient filter, a valve that sticks, a sensor that drifts out of calibration. Over months, small inefficiencies become serious problems. Food adds another layer of complexity. Packaged food degrades over time. Nutritional content changes. Variety matters for mental health as much as physical health. Eating the same meals repeatedly may seem tolerable at first, but over long durations it can affect appetite, morale, and overall well-being. This is why long missions increasingly focus on some degree of food production. Growing plants provides fresh nutrition, psychological comfort, and oxygen recycling. But plants require water, light, nutrients, and careful management. They introduce biological variables into an already complex system. Mold, pests, and disease can spread quickly in closed environments. Survival becomes an exercise in balance. Then there is temperature. Space is not uniformly cold or hot. It is extreme in both directions. Spacecraft must manage heat generated by onboard systems while protecting occupants from the cold vacuum outside. Thermal control systems must function flawlessly for long periods, adapting to changes in orientation, distance from the Sun, and internal activity. Mars adds additional complications. During transit, thermal conditions are relatively stable. On the surface, temperature swings can be severe. Systems must adapt from the controlled environment of space to a planet with day-night cycles, seasons, and weather. All of this depends on power. Power generation during transit typically relies on solar panels or nuclear sources. Solar panels must be oriented, kept clean, and maintained. Dust accumulation can reduce efficiency. Mechanical failures can reduce output. Power shortages cascade quickly. Life support, communication, temperature control, and navigation all depend on reliable energy. Nuclear power offers stability but introduces other risks and political considerations. No option is simple. Survival also has a psychological dimension that cannot be engineered away. Humans are social, adaptable, and resilient, but they are not infinitely so. Extended isolation affects mood, cognition, and behavior. Confined spaces limit privacy. Repetitive routines dull motivation. Delayed communication alters relationships with Earth. A Mars crew would live in close quarters with the same small group of people for years. Conflicts cannot be escaped. Silence can feel heavy. Even positive emotions can become muted over time. Designing habitats that support mental health is as important as designing them to support life support systems. Lighting matters, colour matters, sound matters. Opportunities for solitude matter. So does a sense of purpose. Mars missions cannot rely on novelty to sustain morale. Novelty fades. What remains is routine. Communication with Earth offers connection, but it is imperfect. Messages arrive delayed. Conversations become staggered. Emotional support arrives after the moment has passed. News from home can feel distant and untouchable. This delayed connection can be protective in some ways, reducing stress from immediate concerns on Earth. But it can also deepen feelings of separation. Birthdays, holidays, and milestones pass out of sync. The crew lives in a different temporal rhythm. Survival requires emotional resilience, not just physical health. There is also the matter of medical care. On Earth, medical emergencies trigger a chain of response. Specialists are consulted, equipment is available, evacuation is possible. On Mars, medical care must be self-contained. Crew members must diagnose and treat conditions without external help. This requires extensive training. Crew members must act as medics, dentists, and emergency responders. Equipment must be compact yet capable. Medications must remain stable over years. Procedures must be performed in reduced gravity with limited space. The unknowns are significant. How does the human immune system respond to years in space? How do wounds heal? How do infections behave? We have partial answers, but not complete ones. Survival planning must assume uncertainty. Then there is the spacecraft itself. Machines age. Components wear. Software develops errors. On Earth, maintenance is routine. In space, maintenance is improvisation. Tools are limited. Replacement parts are finite. Crew members must diagnose problems in systems they did not design, often guided by delayed advice from Earth. The longer the journey, the more opportunities for failure. This does not mean failure is likely, but it means preparedness must be exhaustive. Mars missions require a mindset shift. Instead of preventing all failures, they must assume failures will occur and design systems that can absorb them. Graceful degradation becomes a goal. Systems must fail slowly, predictably, and in ways that allow intervention. This philosophy differs from the moon missions, which emphasize performance over longevity. Lunar systems were not designed to last years. Mars systems must. Survival also includes something more subtle, monotony. Long journeys compress variety. The same walls, the same faces, the same tasks. Over time, this sameness can become draining. Motivation must be sustained intentionally. Small rituals matter. Marking time matters. Celebrating progress matters. This is not indulgence. It is maintenance. The human brain evolved for changing environments, social interaction, and sensory richness. Spaceflight removes many of those inputs. Mars missions must compensate deliberately or risk cognitive and emotional decline. Surviving the journey also means surviving boredom. This may sound trivial compared to radiation or system failure, but it is not. Boredom erodes attention. Reduced attention increases error. Error increases risk. The chain is real. Training helps. Selection helps. But design matters too. Survival planning must also account for the unexpected. Solar storms can spike radiation levels suddenly. Micrometeoroids can damage hulls. Software glitches can cascade. No plan survives unchanged. On the Moon, unexpected events were endured briefly. On Mars, they must be managed repeatedly. This is why Mars missions emphasize autonomy. Crews must be able to make decisions without immediate oversight. This autonomy is empowering, but it also places heavier responsibility on individuals. Decision fatigue becomes a factor. Judgment must be preserved. Survival in this context is not heroic. It is disciplined. It involves doing small things correctly every day. Checking systems, exercising, eating properly, communicating clearly, managing conflict, sleeping regularly, maintaining routines even when motivation wanes. The Moon allowed humans to experience space as an intense but brief challenge. Mars requires living with space as a condition. This distinction changes everything. When people imagine Mars missions, they often picture the destination, the red landscape, the first steps, the sense of arrival. But survival is about the long stretch in between, the months where nothing changes dramatically, but everything matters. That stretch is where missions succeed or fail quietly. Survival is not a separate problem from distance, landing, or return. It is the thread that runs through all of them. Every choice about fuel, habitat design, crew size, and mission duration ultimately feeds into the same question. Can humans remain healthy, capable, and mentally whole long enough to do what they came to do and then leave? Long before the first rocket ever left Earth, humans learned that distance does not only stretch landscapes, it stretches the mind. Long journeys change how people think, feel, and relate to one another, even when the road is familiar and the destination is known. Deep space magnifies this effect in ways that are subtle at first, then quietly persistent. When people imagine space travel, they often focus on physical danger, explosions, radiation, mechanical failure. These risks are real, but they are not the only ones that matter. For a mission to Mars, the mind becomes just as critical a system as the engines or life support. And unlike hardware, the mind cannot be swapped out, rebooted, or fully shielded. The Moon missions offered only a brief glimpse of this challenge. Astronauts experienced isolation, confinement, and stress, but for days, not years. They worked under intense pressure, but always with the knowledge that home was close and the mission short. Mars removes that temporal boundary. The mind must adapt not to an episode, but to a condition. The first psychological shift begins with separation. Leaving Earth is not simply a physical departure. It is a gradual uncoupling from the rhythms that quietly organize daily life. Sunrises and sunsets still exist on a spacecraft, but they are artificial. The sounds of weather disappear. The subtle cues that anchor time and place fade. What remains is routine, enforced by schedules rather than environment. At first, this structure can feel comforting. Clear tasks, clear goals, clear roles. But over time, structure without variation can become constraining. Days blur, weeks lose distinction. Without careful attention, time begins to feel both slow and compressed. A strange combination where nothing seems to happen, yet months pass. This altered sense of time affects motivation. On Earth, progress is reinforced by visible change. Seasons shift. Projects reach milestones. Social feedback provides momentum. In deep space, progress is abstract. You are traveling, but you're not arriving. You're working, but the outcome remains distant. Mars missions ask the human brain to tolerate prolonged anticipation. Anticipation is not neutral. It consumes cognitive and emotional energy. Waiting for something important, especially when the wait is long and unavoidable, creates a background tension. It is not panic. It is not fear. It is a low-level alertness that never fully turns off. Over weeks, this tension can erode focus. Over months, it can shape mood. Over years, it can influence identity. Another shift comes from confinement. Spacecraft are small by necessity. Every cubic meter is accounted for. Privacy exists, but it is limited. Sound travels easily. Movement is constrained. There is no opportunity to step outside for a walk, to change scenery, to be alone without being observed. On short missions, this is tolerable. On long missions, it becomes a defining feature of daily life. Humans regulate emotions partly through space. We move away when overwhelmed. We seek closeness when comforted. In deep space, these options are constrained. Interpersonal dynamics are intensified because there is no escape from them. Small irritations that would dissipate on Earth can linger. Habits become noticeable. Differences in communication styles become more pronounced. Conflict does not need to be dramatic to be draining. Even minor friction consumes mental energy when it cannot be resolved through distance. Mars missions require crews not just to coexist, but to remain cooperative and empathetic under sustained pressure. This is not a matter of goodwill alone. It requires training, selection, and design that acknowledge human limits rather than denying them. Delayed communication adds another layer. On Earth, emotional regulation is supported by immediacy. When something goes wrong, we talk to someone, we receive feedback, we adjust. In deep space, communication with Earth is delayed and intermittent. Conversations unfold across minutes or hours. Emotional support arrives out of sync with the moment it is needed. This delay can make Earth feel distant in a way that is more emotional than physical. Messages become archival rather than conversational. By the time a response arrives, the emotional context may have shifted. Crew members must learn to self-regulate more than they ever have before. They must resolve issues internally. They must make decisions without reassurance. This autonomy is empowering, but it is also isolating. There is a particular kind of loneliness that comes from knowing you are heard, but not in real time. The mind also responds to risk differently when risk is constant. On Earth, danger is usually intermittent. It spikes, then recedes. In space, danger is ambient. Radiation exposure continues. Mechanical systems operate near their limits. Escape options are non-existent. Even when nothing is actively wrong, the awareness of vulnerability persists. This does not necessarily cause fear, but it can cause vigilance. Vigilance is mentally taxing. Maintaining attention over long periods without resolution leads to fatigue. Fatigue reduces cognitive flexibility. Reduced flexibility increases the likelihood of errors. This is why psychological resilience is not about toughness, it is about recovery. Mars missions must be designed to allow mental recovery even when external conditions do not change. This means meaningful rest, not just sleep. It means variation in tasks. It means opportunities for autonomy and creativity within structure. Routine, while necessary, must not become rigid. There is also the challenge of monotony. The brain craves novelty. Not excitement necessarily, but variation. On long space missions, novelty is scarce. The environment does not change. New stimuli are limited. Even experiments and tasks eventually become familiar. Monotony does not announce itself as boredom immediately. It creeps in quietly. Attention drifts. Motivation dips. Tasks take more effort. Errors become more likely. Combating monotony requires intentional design, changing lighting patterns, rotating responsibilities, introducing new activities at planned intervals. Even small changes can have outsized effects on mental well-being. On Earth, novelty is abundant. In space, it must be engineered. Then there is the question of identity. On long missions, especially those beyond Earth orbit, individuals may begin to feel suspended between roles. They are no longer fully part of Earth society, yet not fully part of something new. Time passes differently for them than for those at home. Life events continue on Earth without their participation. This can create a sense of dislocation, not just being far away, but being out of phase. Mars crews will miss birthdays, funerals, celebrations, and transitions. They will return to an Earth that has changed. Relationships may feel altered. Roles may need renegotiation. Anticipating this reintegration is part of mental health planning. The mission does not end at landing or even at return. Psychological adjustment continues afterward. The mind in deep space also responds to the absence of natural sensory input. Earth provides constant, subtle stimulation. Wind, smells, variations in temperature, background noise. Spacecraft environments are controlled and uniform. Air smells recycled. Temperature is regulated. Sound is mechanical. Over time, this sensory deprivation can affect mood and cognition. Introducing varied sensory experiences becomes important. Visual variety, music, textures, even simulated nature can help. These interventions are not distractions. They are maintenance. Sleep deserves special attention. Sleep in space is already challenging. Microgravity alters body orientation. Noise persists. Light cycles are artificial. On long missions, sleep disruption can accumulate into chronic fatigue. Fatigue affects judgment, reaction time, and emotional regulation. Mars missions must protect sleep as a priority, not a luxury. Lighting systems that mimic natural cycles, quiet zones, structured schedules that respect circadian rhythms as much as possible. Partial gravity on Mars may help, but the transition itself is disruptive. The body must adapt again. Sleep patterns may shift. Recovery takes time. Another psychological factor is meaning. Humans tolerate hardship better when it feels purposeful. Mars missions are rich in meaning at the abstract level. Exploration, discovery, advancement. But meaning must also be sustained daily. Crew members must feel that their work matters, that progress is real, even when the destination is far away. This requires transparency, autonomy, and recognition. Feeling like a passive passenger erodes morale. Feeling like an active contributor supports resilience. This is why Mars mission planning emphasizes crew involvement in decision-making. Autonomy is not just practical, it is psychological. There is also fear of the unknown, even when it is well studied. Mars is familiar through images and data, but living there is unprecedented. The first crew will encounter situations no one has experienced before. Uncertainty cannot be eliminated, it must be tolerated. Tolerance of uncertainty is a psychological skill. It varies between individuals. It can be trained, but not perfected. Crew selection becomes critical here. Technical skill is necessary but not sufficient. Emotional intelligence, adaptability, and communication skills matter just as much. This is not about heroism. It is about compatibility. The mind in deep space also carries responsibility differently. Decisions matter more when consequences unfold slowly and cannot be undone. This can create decision fatigue. Choosing when to intervene, when to wait, when to conserve resources, and when to act requires constant judgment. Mars missions cannot rely on instinct alone. They must support decision-making through tools, procedures, and shared responsibility. Burnout is a real risk. Long-duration missions concentrate effort without the usual markers of completion. There is no weekend in the usual sense. There is no vacation. Rest must be embedded into routine deliberately. Ignoring this reality does not make it disappear. It makes it more dangerous. One of the most important lessons from space psychology research is that problems rarely appear suddenly. They build gradually. Subtle changes in mood, slight withdrawal, increased irritability, reduced communication. Mars missions must include systems for monitoring mental health continuously, without stigma. Crew members must feel safe acknowledging strain. Support must be proactive rather than reactive. The Moon did not require this level of attention. Mars does. And yet, it is important not to frame the mind in deep space as fragile. Humans are remarkably adaptable. With the right preparation, support and design, people can thrive in extreme environments. Polar stations, submarines and space stations offer evidence of this. Mars is not unique in its demands. It is unique in their duration and irreversibility. As the journey unfolds, the mind becomes both a challenge and a resource. Creativity, cooperation, humor and meaning are not optional extras. They are survival tools. Understanding this shifts how we think about Mars missions. They are not just engineering projects. They are social experiments, psychological experiments, cultural experiments. Every choice about habitat layout, crew size, mission duration, and autonomy shapes the mental landscape as much as the physical one. As we continue forward, this perspective will inform every other challenge we examine. Technology can fail visibly. The mind fails quietly. It does not break. It erodes. Mars does not attack the mind directly. It waits. It stretches time. It removes familiar supports. It asks humans to remain themselves in an environment that does not reflect them back. Surviving the journey, then, is not just about keeping bodies alive. It is about keeping minds engaged, balanced, and connected across a distance that resists connection. And as the spacecraft drifts onward, far from Earth and not yet at Mars, the greatest work happening inside it may not be mechanical or scientific, but human, unfolding slowly in thoughts, relationships, and the daily effort to stay present in a place where nothing changes quickly, yet everything depends on the ability to endure. Life support is one of those phrases that sounds technical and distant until you sit with what it really means. It is not a system that enhances comfort or efficiency. It is the thin boundary between living and not living in a place that offers none of what the human body needs on its own. Air, water, pressure, temperature. Remove any one of them and survival ends quickly. On Earth, these requirements are so constant that they fade into the background. On a Mars mission, they become the background. During the Moon missions, life support was demanding but finite. Systems needed to function for days. Margins were tight but timelines were short. If something behaved strangely, astronauts could tolerate it briefly. Knowing that the end of the mission was close, Mars does not offer that grace. Life support systems for Mars must function continuously, autonomously, and reliably for years, not because that is ideal, but because there is no alternative. The first and most fundamental requirement is air. Humans need oxygen at a precise concentration and pressure range to function normally. Too little oxygen leads to confusion and unconsciousness. Too much becomes toxic over time. Carbon dioxide, a natural byproduct of breathing, must be removed continuously. On Earth, plants, weather, and vast atmospheric processes manage this quietly. On Mars, every breath must be accounted for. Modern spacecraft recycle air using chemical and mechanical systems. Carbon dioxide is scrubbed from the air, and oxygen is replenished through stored supplies or chemical reactions. These systems work well, but they are not trivial. They rely on filters, catalysts, valves, sensors, and software, all of which must perform reliably for long periods. On short missions, redundancy is straightforward. On long missions, redundancy becomes a balancing act. Every backup system adds mass. Every kilogram adds cost and complexity. Yet without redundancy, failure becomes fatal. Mars missions push life support design toward closed-loop systems. Instead of discarding waste and relying on resupply, everything must be reused. Carbon dioxide becomes a resource rather than a waste product. Water vapor from breath is captured and condensed. Oxygen is generated through chemical processes. The system must approach self-sufficiency as closely as possible. Self-sufficiency, however, is not the same as simplicity. Closed-loop systems are complex by nature. They must remain balanced. Small inefficiencies can accumulate. A filter that removes slightly less carbon dioxide than expected will slowly raise levels in the habitat. A sensor that drifts out of calibration can mislead the crew. Over weeks or months, these small deviations can become dangerous. This is why Mars life support must be designed not just to operate, but to be monitored, adjusted, and repaired by the crew themselves. Water presents a similar challenge. Humans need water constantly. Drinking, hygiene, food preparation, cooling systems. On the Moon, water use was carefully rationed, but mission durations were short. Mars missions cannot rely on stored water alone. The mass would be prohibitive. Instead, water must be recycled aggressively. Modern space systems already recycle water from urine, sweat, and humidity. The technology is effective, but it requires careful maintenance. Filters clog, membranes degrade, microorganisms can grow. Water recycling systems must operate without interruption and without introducing contamination. Clean water is not optional. Even minor contamination can cause illness. Illness on Mars is not just uncomfortable, it is dangerous. This is where life support begins to intersect with medical risk. A gastrointestinal infection that would be inconvenient on Earth could compromise hydration, nutrient absorption, and crew performance on Mars. Medical treatment options are limited. Prevention becomes critical. Life support systems must therefore integrate sanitation as well as recycling. Waste handling must be safe, efficient, and psychologically tolerable. No one thrives in an environment where basic hygiene is compromised. Temperature control is another quiet requirement that becomes central in deep space. The human body functions within a narrow temperature range. Spacecraft generate heat internally from electronics and life support systems. They lose heat to space through radiation. Balancing these flows requires active thermal control. On Earth, excess heat dissipates naturally. In space, it must be managed deliberately. Mars adds complexity. During transit, thermal conditions are relatively stable. On the surface, temperatures fluctuate widely between day and night. Dust storms can block sunlight, reducing solar heating. Equipment must adapt without exposing the crew to dangerous extremes. Thermal control systems must be reliable, flexible, and repairable. A failure that leads to overheating or freezing can escalate quickly. On Earth, temperature discomfort is an annoyance. On Mars, it can be lethal. Pressure is another invisible but essential factor. Humans require a pressurized environment to breathe normally. Spacecraft and habitats must maintain internal pressure against the vacuum of space or the thin Martian atmosphere. Pressure leaks are among the most dangerous failures imaginable. They may be slow and subtle or sudden and catastrophic. Detecting and repairing leaks requires constant vigilance. Sensors must be accurate. Crew members must be trained to respond calmly and effectively. Tools must be available. Materials must withstand long-term stress without cracking or degrading. Mars habitats must endure not only internal pressure, but external conditions. Dust, temperature cycling, radiation, and potential micrometeoroid impact all contribute to wear. Unlike orbital habitats, Mars habitats cannot rely on easy replacement or external repair missions. Life support also includes lighting. Light affects more than vision. It influences circadian rhythms, mood, and hormonal regulation. In space, natural light cycles are absent or artificial. Mars days are slightly longer than Earth's, which can disrupt sleep patterns over time. Lighting systems must simulate natural rhythms as closely as possible. Bright light during work periods, dimmer light during rest, color temperature adjustments to cue wakefulness or relaxation. These details matter. Sleep disruption undermines mental and physical health. Food production intersects with life support in increasingly important ways. On Mars missions, growing food is not just about nutrition. Plants recycle carbon dioxide into oxygen. They help regulate humidity. They provide psychological comfort through colour, texture, and growth. Watching something living respond to care can be grounding in an otherwise mechanical environment, but growing food is demanding. Plants require light, water, nutrients, and stable conditions. They are sensitive to changes in temperature, humidity, and microbial balance. A failed crop is not just a disappointment, it is a loss of resources. Balancing food production systems with other life support demands requires careful integration. Power must be allocated, water must be shared, waste products must be managed. Each system interacts with the others. This interdependence is one of the defining features of life support without Earth. On Earth, systems are buffered by scale. If one part falters, others compensate. On Mars, buffers are minimal. Feedback loops are tight. Changes propagate quickly. Life support must therefore be resilient, not just efficient. Resilience means the ability to absorb shocks, adapt to change, and continue functioning even when parts fail. This requires redundancy, modularity, and human involvement. Crew members must understand the systems deeply, not as operators following checklists, but as caretakers capable of diagnosing and improvising. This is a different relationship with technology than most people are accustomed to. On Earth, systems are hidden. In space, they are intimate. You hear them, you monitor them, you depend on them. Psychologically, this constant awareness can be stressful. Knowing that every breath passes through machinery can heighten anxiety, especially early in the mission. Over time, familiarity helps, but the awareness never fully disappears. Design must account for this mental load. Noise matters, alarms matter, interface clarity matters. Systems that constantly demand attention drain cognitive resources. Well-designed systems fade into the background without becoming invisible. Life support without Earth also means life support without rescue. On Earth, if a system fails catastrophically, evacuation is possible. On Mars, evacuation is not. This changes how failure is perceived. It is not an inconvenience, it is a crisis. This reality forces conservative design choices. Proven technologies are favoured over novel ones. Extensive testing is required. Margins are built in wherever possible. Progress slows, but safety increases. Some critics view this caution as excessive, but it reflects the cost of failure. A failed life support system on Mars does not end a mission, it ends lives. Another often overlooked aspect is adaptability. Life support systems must adapt to changing conditions over the mission. Crew size may change temporarily due to illness. Activity levels may vary. Environmental conditions may shift. Systems must respond dynamically without destabilizing. This requires intelligent control systems, robust sensors, and human oversight. Automation helps, but automation must be transparent. Crew members must understand what the system is doing and why. Black boxes breed mistrust. Trust between humans and life support systems is essential. Life support also extends to waste management in ways that are both practical and psychological. Human waste must be processed safely, efficiently, and discreetly. On Earth, this is handled by infrastructure that we rarely think about. On Mars, waste processing is immediate and visible. Odours, contamination risk, and system reliability all matter. Poor waste management degrades quality of life quickly. It affects morale, health, and trust in the environment. Designing waste systems that are robust and tolerable is as important as designing oxygen generators. Life support without Earth also means without ecosystems. On Earth, ecosystems absorb mistakes. Overuse of resources can be mitigated by natural cycles. Pollution can be diluted. On Mars, there is no dilution. Everything circulates within a closed environment. This requires discipline. Resource use must be monitored. Waste must be minimized. Crew members must be aware of the impact of their actions on the system as a whole. This awareness can foster cooperation, but it can also feel constraining. Every action matters. There is little room for carelessness. Mars life support systems must therefore support not just survival, but livability. Living for years in a fragile environment requires more than meeting minimum requirements. It requires comfort, dignity, and a sense of control. Small comforts matter more when options are limited. The Moon did not require this level of attention. Missions were short. Discomfort was tolerated. Mars demands a higher standard because the cost of discomfort accumulates. This is one reason Mars mission planning takes so long. Life support systems must be integrated, tested, and trusted. Failures on Earth during testing are valuable. Failures on Mars are unacceptable. Mars is not just far away. It is far away from support systems that humans take for granted. Every function Earth provides automatically must be recreated deliberately. Air must be made, water must be recovered, waste must be transformed, heat must be balanced, light must be simulated, health must be preserved. Life support without Earth is not a single system. It is an entire artificial world compressed into a small volume, expected to function continuously in an environment that offers no assistance. The Moon allowed us to visit space briefly. Mars asks us to live there, and living there means accepting that survival depends not on heroism or endurance alone, but on the quiet, constant cooperation between human needs and machines that never get a day off, carrying life forward, breath by breath, cycle by cycle, as the distance from Earth remains vast and the responsibility to keep that artificial world intact becomes the most important task of all. Dust is easy to underestimate. On Earth it is mostly an inconvenience. It settles on shelves, coats, shoes, clogs filters, and then gets wiped away or washed out by rain. It behaves predictably. Gravity pulls it down, weather clears it away. On Mars, dust does not play by those rules, and that difference quietly turns it into one of the most persistent and underestimated obstacles to human survival. The Moon has dust too, and lunar dust caused real problems. It was sharp, abrasive, and irritating. It scratched visors, wore down seals, and clung stubbornly to suits and equipment. Astronauts brought it back inside with them, where it floated briefly in low gravity and irritated eyes and lungs. But lunar dust had one redeeming quality. Once it settled, it stayed put. With no atmosphere, no wind, and low gravity, dust did not migrate on its own. It was a problem you carried, not a problem that followed you. Mars dust is different. Mars dust moves, it drifts, it floats, it creeps. It finds its way into places it was never invited and refuses to leave. This behaviour is not dramatic most of the time. It does not arrive as a sudden disaster. It accumulates slowly, quietly, and persistently, which is exactly what makes it dangerous over long missions. Martian dust is incredibly fine. The particles are much smaller than typical sand grains, closer in size to smoke or flour. This allows them to remain suspended in the thin Martian atmosphere far longer than dust on Earth would. Even gentle winds can lift them. Once airborne, they can travel vast distances, circling the planet during seasonal storms. This dust is also electrostatically charged. As particles rub against each other in the dry Martian environment, they build up static electricity. That charge makes them cling to surfaces aggressively. Solar panels, camera lenses, joints, seals, radiators, and spacesuit fabric all become targets. Dust does not simply fall off when shaken, it sticks, often resisting cleaning methods that work perfectly well on Earth. For robotic missions, this has already proven to be a serious issue. Solar-powered rovers have seen their energy output decline as dust slowly coats their panels. In some cases, missions expected to last months were extended by years only because occasional dust devils passed by and cleaned the panels unexpectedly. That reliance on chance is not a strategy humans can accept. For human missions, dust is not just an engineering nuisance, it is a health concern. Fine dust particles can be inhaled easily. On Earth, lungs have evolved to handle a wide range of airborne particles, but Martian dust is chemically reactive. It contains compounds that may irritate tissue or interfere with biological processes. Prolonged exposure, especially in a closed habitat, could cause respiratory problems, inflammation, or long-term health effects that are still not fully understood. Mars missions cannot afford to discover these effects through trial and error. Dust also interacts with machinery in ways that compound over time. It works its way into moving parts. Hinges, bearings, seals, and joints all suffer gradual wear as fine particles infiltrate and grind away at surfaces. Lubricants degrade, friction increases. Systems that worked perfectly during initial testing begin to behave unpredictably months later. On Earth, this kind of wear triggers maintenance cycles and part replacement. On Mars, replacement options are extremely limited. Every system must tolerate dust exposure for long periods without failing. This requirement influences everything from rover wheels to habitat airlocks. Airlocks are a particular challenge. Every time an astronaut returns from outside, dust comes with them. No matter how careful the procedure, some dust will cling to suits and equipment. Once inside the airlock, gravity is enough to pull some of it down, but much of it remains suspended or settles into corners and seams. Over time, airlocks can become contamination points, spreading dust into living spaces unless actively managed. Designers must consider suit ports, specialized docking systems that keep spacesuits outside the main habitat, reducing dust transfer. These systems are promising, but they are complex and must function flawlessly. A malfunctioning suit port is not just inconvenient. It can delay activities or compromise safety. Dust also affects thermal control. Radiators used to shed excess heat rely on clean surfaces to function efficiently. A thin layer of dust can significantly reduce their effectiveness. As dust accumulates, heat builds up. Overheating stresses electronics, life support systems, and power systems. Temperature control becomes harder, requiring more energy to compensate. That extra energy must come from somewhere. Solar panels are particularly vulnerable. Dust accumulation reduces sunlight absorption, lowering power output. Reduced power affects everything downstream. Life support, communication, heating, food production. Power shortages cascade quickly. On Mars, dust storms can last weeks or even months, reducing sunlight dramatically. During these periods, solar power becomes unreliable. Nuclear power sources can help, but they introduce other constraints and are not immune to dust-related mechanical issues. Even optics suffer. Cameras, sensors, and scientific instruments rely on clear surfaces. Dust reduces resolution, distorts measurements, and obscures hazards. For human missions, situational awareness is critical. Visibility matters during driving, construction, and exploration. Dust on visors and sensors compromises safety. Cleaning these surfaces is not straightforward. Wiping can scratch coatings. Blowing dust away may not work due to static cling. Using liquids introduces freezing and contamination risks. This means dust mitigation must be designed into systems from the start, not added later as a workaround. The behavior of Martian dust also complicates landing and ascent. During landing, engine exhaust kicks up dust, creating dense clouds that obscure sensors and cameras. This can confuse navigation systems at the very moment precision matters most. Autonomous systems must be able to land safely even when visibility drops suddenly. After landing, dust settles unevenly, coating surfaces and filling crevices. Before ascent, engines must ignite in an environment filled with loose particles. Dust ingestion into engines can damage components or reduce efficiency. Protective covers and careful sequencing are required, adding complexity and potential failure points. Mars dust also affects human movement. Unlike lunar dust, which falls quickly in low gravity, Martian dust remains airborne longer. Walking, driving, or even opening doors can stir it up. Over time, this creates a persistent haze around activity areas, increasing exposure and reducing visibility. Habitat interiors must be protected aggressively. Air filtration systems must remove fine particles continuously. Filters must be replaced or cleaned regularly. Filter failure leads to contamination of living spaces, increasing health risks. Air filtration itself introduces challenges. Fine dust clogs filters quickly. Clogged filters reduce airflow, increasing strain on fans and compressors. Maintenance becomes frequent. Crew time is consumed by cleaning rather than exploration. Dust also has a psychological impact. Living in an environment where cleanliness is constantly under threat can be stressful. The sense that no matter how careful you are, contamination persists, erodes comfort. Dust becomes a reminder that the environment is hostile and invasive. On Earth, you can escape dirt by going inside. On Mars, dust follows you inside unless extraordinary measures are taken. This constant battle against the environment contributes to fatigue. It adds to the workload. It reinforces the feeling that Mars is not a passive backdrop, but an active participant in daily life, one that resists human presence at every step. Even clothing is affected. Fabric choices must account for abrasion and dust adhesion. Ordinary materials degrade quickly. Specialized fabrics help, but they are not immune. Suits become heavier as dust accumulates. Joints stiffen. Mobility decreases. Maintenance time increases. Over months and years, this wear must be managed deliberately. Spare suits, repair kits, and cleaning procedures must be planned in advance. Running out of functional suits limits exploration and increases risk. Dust also interacts with electronics in subtle ways. Fine particles can cause electrical shorts, interfere with sensors, and degrade connectors. Static discharge can damage components. Shielding helps, but shielding adds mass and complexity. Again, everything connects. The Moon allowed humans to encounter dust as a nuisance. Mars turns dust into an environmental constant. It is not something you encounter occasionally. It is something you live with every day. This distinction matters because Mars missions are not short visits, they are long stays. Small problems that would be tolerable for a week become serious over years. This is why dust mitigation is one of the most active areas of Mars research. Engineers study coatings that repel dust, electrostatic systems that shake particles loose, mechanical brushes and wipers, magnetic fields. None of these solutions is perfect. Each has trade-offs. Coatings degrade. Moving parts fail. Power consumption increases. Systems interact in unexpected ways. The challenge is not eliminating dust. That is impossible. The challenge is managing it well enough that it does not dominate the mission. Mars dust also behaves differently depending on location and season. Some regions experience frequent dust activity, others are relatively calm. Choosing landing sites involves balancing scientific interest, safety, and dust exposure. A site with valuable geology may be more prone to storms. A safer site may be less interesting scientifically. Compromise becomes unavoidable. This dynamic reinforces a broader theme of Mars exploration. Mars does not offer ideal conditions. Every choice involves trade-offs. Dust is one of the clearest examples because it touches so many systems at once. For robotic missions, dust has already shaped outcomes. Some missions ended early due to power loss. Others survived only because of luck. Humans cannot rely on luck. Human missions require dust management strategies that are robust, redundant, and deeply integrated into daily operations. Cleaning must be routine. Monitoring must be continuous. Response plans must exist for worst-case scenarios. Dust storms, while dramatic, are not the only concern. The daily, low-level accumulation is often more dangerous. It is easier to respond to a storm than to a slow decline. The tyranny of dust lies in its patience. It does not rush, it does not attack. It waits, accumulates, and interferes quietly until systems degrade and options narrow. Understanding this reframes the idea of Mars as a dusty desert. It is not just a surface characteristic, it is a planetary behavior that affects atmosphere, climate, and every human-made system placed there. The Moon tested our ability to tolerate dust briefly. Mars tests our ability to manage it indefinitely. Dust is not a single problem to be solved. It is a condition to be lived with. And in an environment where survival depends on machines functioning smoothly, lungs remaining clear, and power systems staying efficient, a fine red powder that refuses to behave becomes more than an annoyance. It becomes a constant reminder that Mars is not empty space waiting to be occupied, but an active world quietly pushing back against every attempt to settle in, particle by particle, day after day, without ever needing to raise its voice. Temperature is one of those things we rarely think about until it stops behaving the way we expect. On Earth, it shifts gently from morning to evening, from season to season. Even extremes are moderated by atmosphere, oceans, and geography. You can dress for the cold, seek shade from the heat, or step indoors and let walls do the work for you. Mars does not offer that kind of cooperation. Temperature there is not a background condition. It is an active force that shapes every moment of survival. The Martian environment looks calm from a distance. Photographs show wide plains, soft hills, and a quiet horizon under a pale sky. There are no raging oceans or towering thunderstorms visible at first glance. That calm is misleading. Mars is harsh not because it is violent, but because it is relentless. Its environment applies pressure steadily, without pause, and without much variation to provide relief. To begin with, Mars is cold. Not occasionally cold, not seasonally cold, but fundamentally cold. The average surface temperature on Mars is around minus 60 degrees Celsius. That number alone sets the tone. Even at its warmest, near the equator at midday during summer, temperatures barely rise above freezing. At night, they can plunge dramatically, dropping by tens of degrees in a matter of hours. These swings happen daily, not just seasonally. This is not a world where cold is an inconvenience. It is the default state. The reason lies largely in Mars's atmosphere, or rather its lack of one. Mars's atmosphere is thin, less than 1% the density of Earth's at the surface. It cannot trap heat effectively. When the sun shines, the surface warms briefly. When the sun sets, that heat escapes quickly back into space. There is no thick blanket of air to slow the loss. For humans, this means that temperature control cannot rely on the environment at all. Every habitat, vehicle, and suit must generate and retain its own warmth continuously. Failure to do so is not uncomfortable. It is fatal. Thermal systems must operate day and night, regardless of weather or activity. Heating elements must be reliable. Insulation must be robust. Power must be available. Any interruption allows temperatures to fall rapidly, stressing equipment and endangering lives. Mars does not give you time to fix heating problems casually. The cold also affects materials in ways that accumulate quietly. Metals contract, plastics become brittle, seals stiffen, lubricants thicken, electronics behave differently at low temperatures. Components that function perfectly on Earth can fail unpredictably after repeated thermal cycling on Mars. This cycling is one of the most difficult aspects of the Martian environment. Temperatures rise and fall sharply each day. Materials expand and contract repeatedly. Over time, this causes fatigue. Micro cracks form. Joints loosen. Connections degrade. On Earth, such wear might take decades. On Mars, it can accelerate. This is why Mars hardware must be tested not just for cold, but for repeated cold. Endurance matters more than peak performance. Systems must survive thousands of temperature swings without losing integrity. The weather adds another layer of complexity. Mars does have weather, though it behaves differently from Earth's. Winds blow across the surface, driven by temperature differences and seasonal changes. While these winds are usually gentle in terms of force, the thin atmosphere means they can still move dust effectively. Over time, wind shapes the landscape, sculpts dunes, and redistributes fine particles across vast distances. Mars is also famous for its dust storms. These storms can be local, regional, or global. Local storms may affect a small area briefly. Regional storms can cover large portions of the planet. Global dust storms can envelop nearly the entire surface, reducing sunlight dramatically for weeks or months. These storms do not bring rain or lightning. They bring opacity. Sunlight dims, shadows soften, solar power drops, temperatures change, atmospheric dynamics shift. For human missions, this means that weather is not just something to observe, it is something to plan around carefully. A global dust storm does not need to be violent to be dangerous. Its danger lies in persistence. Reduced sunlight affects power generation. Lower power affects heating, life support, and food production. Systems must be able to endure long periods of reduced energy input. On Earth, storms pass and infrastructure recovers. On Mars, recovery must be built in from the start. Mars's weather also changes slowly. Storms can take weeks to develop and weeks to dissipate. There is little warning in the human sense. Robotic missions have taught us that storms can appear unexpectedly and linger longer than anticipated. This unpredictability complicates mission planning. Activities that rely on solar power, visibility, or stable temperatures must be flexible. Rigid schedules are fragile. Adaptability becomes essential. Seasonal changes add further complexity. Mars has seasons similar to Earth's, caused by its tilted axis. But Mars's year is almost twice as long as Earth's, meaning each season lasts much longer. Winter is not a brief inconvenience, it is a prolonged condition. Temperatures drop further, dust activity changes, atmospheric density fluctuates. These seasonal shifts affect landing sites differently depending on latitude. Regions closer to the poles experience more extreme temperature swings. Equatorial regions are more stable, but still far harsher than anything humans experience routinely. Choosing where to live on Mars involves balancing many factors: temperature stability, sunlight availability, dust activity, scientific interest, accessibility. No location offers everything, every site demands compromise. The Martian environment also includes radiation, which interacts with temperature and weather in subtle ways. Mars lacks a strong global magnetic field. This means that high-energy particles from space reach the surface more easily. The thin atmosphere offers little protection. Radiation exposure remains high year-round, regardless of weather. However, temperature affects how radiation impacts materials. Cold conditions can exacerbate radiation damage in electronics. Thermal stress combined with radiation accelerates degradation. Systems must be designed to tolerate both simultaneously. Human habitats must shield occupants from radiation while maintaining thermal stability. Thick walls help with radiation but increase mass. Insulation helps with temperature but can trap heat unevenly. Balancing these requirements is not trivial. Then there is pressure. Mars's atmospheric pressure is extremely low, less than 1% of Earth's. Liquid water cannot exist stably on the surface. This low pressure also affects how heat is transferred. Convection, the process that helps distribute heat through air, is weak. This means that hot and cold spots can form easily inside structures if not managed carefully. Thermal control systems must circulate air actively to maintain even temperatures. Fans and ducts must operate continuously. If circulation fails, localized cold zones can develop quickly, affecting comfort and equipment reliability. On Earth, thermal gradients are moderated by thick air. On Mars, they must be engineered away deliberately. Weather on Mars also includes phenomena that are unfamiliar to humans. Dust devils, for example, are common. These small whirlwinds form when warm air rises rapidly through cooler surrounding air. They can travel across the surface, lifting dust high into the atmosphere. Dust devils can be helpful or harmful. They have cleaned solar panels on robotic missions, restoring power unexpectedly. They can also deposit dust elsewhere, interfere with visibility, and contribute to erosion. Human missions cannot rely on dust devils for cleaning. They must design systems that tolerate their effects without depending on them. Temperature affects human performance directly. Cold environments increase energy expenditure. The body burns more calories to maintain warmth. Muscles stiffen. Dexterity decreases. Reaction times slow. Even inside heated habitats, temperature gradients can affect comfort and productivity. Spacesuits must maintain internal temperature precisely. Too warm, and the astronaut overheats. Too cold, and manual tasks become difficult. Managing heat inside a suit is surprisingly challenging. Physical activity generates heat quickly. External temperatures may be extremely low. Heat must be removed without freezing. On Mars, this balance must be maintained during long surface operations. Exploration is not a short excursion. Tasks may last hours. Equipment must function reliably throughout. Weather also influences scheduling. Mars missions cannot assume that every day is suitable for outdoor activity. Dust storms reduce visibility and power. Extreme cold increases risk. Winds may interfere with operations. Planning must include contingency days and flexible objectives. This requires patience and restraint. Pushing through adverse conditions increases risk without necessarily increasing reward. The Martian environment also affects sound, light, and perception. The thin atmosphere transmits sound poorly. Sounds are quieter and higher pitched. This may seem trivial, but it affects communication during surface operations. Verbal cues are harder to hear. Situational awareness changes. Light behaves differently too. The sky appears butterscotch-coloured due to suspended dust. Shadows are softer. Visual contrast is reduced. Depth perception can be affected. Over time, this unfamiliar lighting may contribute to eye strain or fatigue. Humans evolved under Earth's lighting conditions. Mars subtly alters those conditions, requiring adaptation. Weather forecasting on Mars is improving, but it is still limited compared to Earth. The data available is sparse. Models are improving, but uncertainty remains. Crews must be prepared to respond to changes with limited warning. This uncertainty feeds back into psychological stress. Knowing that the environment can change slowly but significantly without clear signals requires constant vigilance. Mars's environment also interacts with time in important ways. Because days and seasons are longer, conditions persist. A cold snap is not brief. A dusty period does not clear overnight. This persistence magnifies the impact of environmental stressors. There is less relief, less reset. On Earth, weather often provides variety. On Mars, it provides endurance tests. The Moon did not require humans to contend with weather. Its environment was static. Temperature extremes existed, but they were predictable and localized. Mars adds dynamics without offering protection. This combination is what makes Mars's environment particularly challenging. It is not extreme in one way. It is moderately hostile in many ways simultaneously. Cold, thin air, dust, radiation, weather. Each alone could be managed. Together they create a system that requires constant attention. Human habitats must be robust against temperature swings. Vehicles must operate reliably in cold and dust. Power systems must endure storms. Life support must compensate for environmental variability. Every system must assume that the environment will test it repeatedly. This testing does not stop. Mars does not settle into a stable pattern that humans can simply adapt to once and be done. Conditions vary daily and seasonally. Wear accumulates, systems age. The environment remains indifferent. Understanding this reframes the challenge of Mars exploration. It is not about surviving a moment. It is about coexisting with an environment that never fully relaxes. This is why Mars missions emphasize sustainability rather than speed. Rushing increases exposure to environmental risk. Careful pacing allows systems to adjust and crews to respond. It is also why Mars exploration leans heavily on preparation. Testing on Earth, simulations, robotic precursors. Each step reduces uncertainty, not because Mars becomes kinder, but because humans become more prepared. The Martian environment does not oppose us actively. It simply exists as it is, cold, dusty, thin, and patient. It does not need to be dramatic to be difficult. Mars is not waiting for us with open arms. It is waiting with conditions, and those conditions, shaped by temperature, weather, and an environment that offers no margin by default, remind us that going to Mars is not about planting a flag and leaving. It is about learning how to live, work, and remain human in a world where warmth must be created, shelter must be earned, and every day requires quiet negotiation with a planet that never promised to be friendly, only consistent in the way it tests anyone who tries to stay. Entry, descent, and landing are often spoken about as if they are a single event, a dramatic sequence that begins when a spacecraft touches the atmosphere and ends when it reaches the ground. In reality, this phase is less like a moment and more like a narrowing corridor. Options disappear quickly, margins shrink. Everything that has been planned for years is compressed into a short span where physics takes over and refuses negotiation. For Mars, this corridor is especially narrow. By the time a spacecraft reaches Mars, it has already travelled for months through deep space. Its systems have aged. Its surfaces have been exposed to radiation and micrometeoroids. Its fuel reserves are carefully rationed. There is no room for last-minute changes. Entry begins with whatever condition the vehicle happens to be in at that exact moment. Unlike Earth, Mars does not offer a forgiving arrival. A spacecraft approaching Mars is moving extremely fast, often faster than anything humans experience in atmospheric flight. This speed is not optional. It is a consequence of falling into the Sun's gravity well and then intersecting Mars's orbit. Slowing down enough to land safely is the core problem, and Mars makes that problem unusually difficult. The Moon simplified this challenge. With no atmosphere, lunar landing was a matter of controlling descent with engines alone. Gravity pulled downward, thrust pushed upward. The environment did not interfere. Mars adds interference without offering help. Mars's atmosphere is thick enough to generate intense heat during entry, but too thin to provide reliable aerodynamic braking. This creates a paradox. You must use the atmosphere to slow down, but you cannot rely on it to finish the job. Heat shields are essential, but heat shields alone cannot bring a heavy spacecraft to a safe landing speed. Parachutes help, but they lose effectiveness quickly in thin air. Engines must take over near the end, but by then fuel margins are tight. Each of these steps must occur in the correct order, at the correct time, under conditions that cannot be fully controlled. Entry begins high above the Martian surface, where the atmosphere is little more than a whisper. At this altitude, the spacecraft starts to encounter air molecules at tremendous speed. Friction builds rapidly. Heat rises. The heat shield absorbs and dissipates this energy, glowing as it does so. This heating phase lasts longer than Earth re-entry. Even though peak temperatures may be lower, Mars's thin atmosphere spreads the heating over a longer time. That prolonged exposure places different demands on materials. Heat shields must endure sustained stress without cracking, delaminating, or eroding unevenly. A flaw here is catastrophic. There is no redundancy for the heat shield. It either works or the mission ends. As the spacecraft descends deeper, atmospheric drag increases. Speed drops, but not enough. Parachutes deploy, often supersonic, inflating violently in thin air. Designing parachutes that can survive this environment is itself a challenge. They must open reliably at extreme speeds, withstand enormous forces, and function in conditions far removed from anything on Earth. Even when parachutes deploy successfully, they cannot slow the spacecraft enough on their own. Mars's atmosphere simply does not provide sufficient resistance. Large parachutes help, but they reach diminishing returns quickly. Making them larger adds mass and complexity without proportionate benefit. This is where engines come back into play. Near the surface, parachutes are cut away, and descent engines fire to provide the final braking. This transition must be timed precisely. Fire too early, and fuel is wasted. Fire too late, and impact velocity is too high. The margin for error is measured in seconds. All of this happens autonomously. Because of communication delays, no human on Earth can intervene during entry, descent, and landing. Commands sent from Earth arrive too late to be useful. Telemetry received on Earth reflects events that have already happened. By the time anyone knows there is a problem, it is already resolved one way or another. This autonomy raises the stakes dramatically. The spacecraft must sense its environment accurately, interpret that data correctly, and execute the right actions without hesitation. Sensors must function despite dust, vibration, and heating. Software must make decisions based on incomplete information. Actuators must respond instantly. For robotic missions, this is challenging enough. For human missions, the complexity multiplies. Human landers are heavier. They carry life support systems, habitats, supplies, and return vehicles. Increased mass means higher momentum. Higher momentum means more energy must be dissipated during descent. Heat shields must be larger, parachutes must be stronger, engines must provide more thrust. Scaling up is not linear. Doubling mass more than doubles difficulty. This is one reason Mars landings have historically been risky even for robots. A significant fraction of attempted Mars landings have failed. These failures were not due to negligence or incompetence. They were due to the environment being unforgiving. Each failure taught valuable lessons, improved guidance, better sensors, more robust software. But human missions cannot afford to learn this way. There is no tolerance for iterative failure when lives are involved. Landing site selection adds another layer of difficulty. Mars's surface is uneven. Craters, rocks, slopes, and cliffs are common. A safe landing zone must be relatively flat, free of large obstacles, and within reach of scientific targets. It must also sit at an elevation that provides enough atmosphere for braking. Lower elevations are safer for landing because the atmosphere is denser. Higher elevations are more interesting scientifically but more dangerous. This trade-off shapes where missions can go. Precision matters. Early Mars missions accepted landing uncertainties measured in kilometers. Modern missions aim for tens of meters. Human missions will require even greater accuracy to land near pre-positioned equipment, habitats, and fuel production systems. Achieving this precision through a dynamic atmosphere with delayed communication demands advanced navigation techniques. Terrain-relative navigation systems compare real-time imagery to onboard maps, identifying hazards and adjusting descent paths accordingly. These systems are powerful, but they must work perfectly. A misidentified feature or a corrupted map could lead to disaster. Then there is the issue of dust during landing. As descent engines fire, they kick up clouds of dust that obscure sensors and cameras. This phenomenon, known as brownout, can blind the lander at the worst possible moment. Autonomous systems must be able to continue landing even when visual information degrades rapidly. Radar and LiDAR can help, but they are not immune to interference. Dust particles scatter signals. Measurements become noisy. Algorithms must distinguish between real obstacles and artifacts. Again, there is no opportunity for human correction. The final seconds of landing are the most unforgiving. Velocity must approach zero. Orientation must be correct. Contact must occur evenly. Landing legs must absorb impact without tipping. All of this must happen on a surface whose properties may differ from expectations. Mars soil varies. Some regions are firm, others are soft. Landing legs must accommodate uneven load distribution. A foot sinking unexpectedly could destabilize the vehicle. For robotic landers, tipping may end the mission. For human landers, it could be catastrophic. After touchdown, the challenges do not immediately end. Systems must transition from descent mode to surface mode. Engines shut down. Power systems reconfigure. Life support stabilizes. Pressure is maintained. If any of these transitions fail, the crew may be in danger before they ever leave the vehicle. This immediate post-landing phase is one of the most stressful periods of the mission. The environment is unfamiliar. Systems are settling. Dust is everywhere. Crew members must verify that everything is stable before beginning surface operations. On the Moon, this process was comparatively simple. Conditions were predictable. Mars adds uncertainty. The entry, descent, and landing problem is not just about physics, it is about sequencing. Dozens of systems must activate and deactivate in precise order. Timing errors propagate quickly. A delay in one system can cascade into failures elsewhere. Testing this sequence on Earth is extremely difficult. Earth's gravity and atmosphere differ. Simulations help, but they cannot replicate every condition. Wind tunnels, drop tests, and high-altitude flights provide partial data. Full validation is impossible until the actual landing occurs. This is why Mars landings are so tense. Every mission represents a leap of faith, grounded in preparation but tested only once. For human missions, this leap must be minimized. Redundancy can help, but redundancy adds mass. Mass adds difficulty. Engineers must choose where to add backups and where to accept risk. Some propose alternative landing methods: inflatable heat shields, supersonic retropropulsion, sky cranes scaled up for humans. Each idea has promise, but each introduces new unknowns. Supersonic retropropulsion, for example, involves firing descent engines while still moving at supersonic speeds in the atmosphere. This approach can reduce reliance on parachutes, but it creates complex interactions between engine exhaust and airflow. These interactions are difficult to model accurately. Testing them at scale is challenging. Inflatable heat shields increase surface area without adding much mass, improving atmospheric braking. But they introduce structural risks. Deployment must be flawless. Materials must withstand prolonged heating. Every solution shifts risk rather than eliminating it. Another challenge is the integration of landing systems with ascent systems. Human Mars landers must eventually launch back into orbit. Landing gear, fuel tanks, engines, and structural elements must support both descent and ascent. This dual-purpose design increases complexity. On the Moon, ascent and descent vehicles were often separate. On Mars, separating them increases mass and mission complexity. Integrating them increases design constraints. Once again, trade-offs dominate. Entry, descent, and landing also influence mission architecture at a higher level. Some proposals involve landing cargo missions years before humans arrive, pre-positioning supplies and fuel. This reduces risk during human landings but increases reliance on precise timing and system longevity. If a pre-positioned system fails after landing but before crew arrival, the mission may be delayed or cancelled. This adds pressure to cargo landings, which must be reliable despite being unmanned. Human missions become dependent on years-old hardware functioning perfectly. This dependency highlights the interconnected nature of Mars exploration. Entry, descent, and landing are not isolated challenges. They link to fuel production, habitat deployment, and return capability. A successful landing is necessary but not sufficient. Mars does not care whether the mission is robotic or human. The same physics apply, the same atmosphere resists, the same gravity pulls, the same dust obscures. What changes is the cost of failure. Robotic missions accept failure as part of exploration. Human missions cannot. This difference slows progress, but it also reflects responsibility. Sending humans to Mars is not a stunt. It is a commitment to bringing them back safely. This is why the entry, descent, and landing problem remains one of the central hurdles in Mars exploration. Not because it is unsolved, but because it is only partially solved, and because scaling solutions up to human missions multiplies complexity in ways that resist shortcuts. The Moon let us land using relatively straightforward methods. Mars demands choreography. Every second matters, every system matters, every assumption is tested. Entry, descent, and landing will always be a narrow corridor. Crossing that corridor successfully requires patience, humility, and acceptance that some problems cannot be rushed into submission. They must be approached carefully, tested repeatedly, and respected for what they are. Mars does not block our arrival outright. It simply demands that we arrive on its terms, and once that demand is met, once a human-rated spacecraft survives those tense minutes and settles onto the surface, the mission will not feel complete. It will feel as though a door has just closed behind the crew, sealing them into the next phase of challenges, where landing is no longer the question, but living, working, and eventually leaving will carry the same weight of precision and consequence that entry demanded, unfolding slowly under a sky that offers no forgiveness for mistakes made too quickly. Nothing about Mars was designed with humans in mind. That may sound obvious, but it is easy to underestimate just how complete that mismatch really is. Mars is not merely inconvenient for human life, it actively excludes it. There is no breathable air, no liquid water on the surface, no protective magnetic field, no stable temperatures, no soil that can support Earth plants without intervention. Every assumption the human body makes about its surroundings fails there. So when we talk about building on Mars, we're not talking about construction in the familiar sense. We're talking about creating an artificial world inside a hostile one, a controlled bubble where biology and machinery must cooperate continuously just to keep people alive. On Earth, buildings work with the environment. They block wind, shed rain, retain heat, and allow air to circulate naturally. Even extreme environments, deserts, polar regions, high mountains, still provide basic atmospheric pressure, oxygen, and gravity that our bodies evolved to tolerate. Mars provides none of these. Any structure placed there must replace almost everything Earth does for us automatically. That replacement begins with pressure. Human bodies are not built to function in low-pressure environments. Without sufficient pressure, oxygen cannot move from lungs into the bloodstream effectively, even if oxygen is present. Mars's atmospheric pressure is so low that unprotected humans would lose consciousness within seconds. Survival depends entirely on sealed habitats that maintain Earth-like pressure inside. This requirement shapes every design choice. Walls must be strong enough to withstand constant outward force. Seals must remain airtight for years. Materials must tolerate repeated stress from pressure differences combined with temperature swings. Even tiny leaks are unacceptable because they do not merely waste air. They reduce pressure slowly but relentlessly. Unlike on Earth, where a draft is an annoyance, on Mars a leak is a system failure. Pressure containment also affects shape. Rectangular rooms are familiar and convenient, but they distribute stress unevenly. Curved surfaces handle pressure more efficiently. This is why many Mars habitat concepts favour cylindrical or dome-like structures. These shapes are not aesthetic choices, they are structural necessities. But curved pressure vessels are harder to divide into familiar living spaces. Furniture must be adapted. Storage becomes less intuitive. Human comfort must be balanced against engineering efficiency. This tension runs through every aspect of building on Mars. Air is the next challenge. Inside a Mars habitat, air must be created, circulated, cleaned, and monitored constantly. Carbon dioxide must be removed. Oxygen must be replenished. Humidity must be controlled. Airflow must prevent stagnant zones where carbon dioxide could accumulate. On Earth, air circulation happens naturally. Warm air rises, cool air sinks. Pressure differences drive flow. On Mars, inside sealed habitats, all airflow must be forced. Fans must run continuously. Ducts must remain clear. Sensors must remain accurate. If circulation fails, localized problems can develop quickly. A corner of a room can become oxygen poor. Carbon dioxide levels can rise without obvious warning. These are not dramatic failures, they are subtle ones, and subtle failures are often the most dangerous. Water follows closely behind. Mars has water, but not in a form humans can easily use. Ice exists below the surface and at the poles. Extracting it requires energy, machinery, and time. Once extracted, water must be purified, stored, and recycled continuously. In a Mars habitat, water is never wasted. Every drop is used repeatedly. Drinking water becomes wastewater. Wastewater becomes recycled water. Recycled water becomes drinking water again. This cycle must continue indefinitely. On Earth, water recycling is supported by vast ecosystems and infrastructure. On Mars, it must be perfect. Contamination is a constant concern. Microorganisms introduced by humans can grow in warm, moist systems. Biofilms can clog pipes. Filters can fail. Sensors can drift. Detecting and correcting these issues requires vigilance and expertise. Water is not just for drinking. It is used for hygiene, food preparation, cooling systems, and plant growth. A shortage affects everything at once. Building a habitat means building a water economy that can survive stress, failure, and time. Then there is temperature. Mars is cold enough to freeze exposed skin almost instantly. Habitats must maintain stable internal temperatures despite extreme external fluctuations. Heating systems must run constantly. Insulation must be effective. Thermal bridges, points where heat leaks out, must be minimized, but heating creates its own problems. Electronics generate heat. Life support systems generate heat. Human bodies generate heat. Without proper heat rejection, habitats can overheat internally even while freezing externally. On Earth, excess heat escapes naturally. On Mars, heat must be actively moved and radiated away. Radiators must function efficiently. Dust accumulation reduces their effectiveness. Power must be available to keep heat flowing where it needs to go. Building on Mars means managing heat as carefully as managing air. Radiation adds another layer. Mars lacks a strong magnetic field, and its thin atmosphere provides little protection from cosmic radiation and solar particles. Over time, radiation exposure increases cancer risk and can damage the nervous system. Habitats must provide shielding. Shielding can be achieved in several ways: thick walls, buried structures, using Martian soil as a protective layer. Each approach has advantages and drawbacks. Thick walls add mass. Burying habitats requires excavation. Soil composition varies. No solution is simple. Shielding also affects habitat design. Windows become liabilities. Views are psychologically valuable, but transparent materials provide less protection. Designers must balance mental health benefits against radiation risk. Some proposals use water as shielding, surrounding living areas with water tanks. This provides radiation protection and integrates water storage into structural design. It is elegant, but complex. Leaks become more dangerous. Structural loads increase. Again, everything connects. Food production introduces biological complexity into an already fragile system. Humans cannot rely entirely on stored food for years without degradation in nutrition and morale. Growing food on Mars supports health and provides psychological benefits. Plants add color, texture, and life to an otherwise mechanical environment. But Mars soil is not Earth soil. It lacks organic matter. It contains chemicals that may be harmful to plants and humans. Growing food requires controlled environments, hydroponic or aeroponic systems, artificial lighting, and careful nutrient management. Plants consume water and power. They require attention. Crops can fail. Pests and diseases can spread rapidly in closed systems. Food production is not just agriculture, it is life support. Habitats must integrate growing spaces in ways that do not compromise air quality, water systems, or power availability. Harvest schedules must align with crew needs. Waste from plants must be managed. On Earth, agriculture exists outdoors, supported by sunlight and rain. On Mars, it exists inside, supported by electricity and machinery. Living space itself becomes a design challenge. Humans need room to move, rest, and feel separate from one another at times. But volume is expensive to launch. Larger habitats require more materials, more shielding, more power. Designers must decide how much space is enough. Too little space increases stress and conflict. Too much space increases risk and cost. There is no clear formula. Habitats must support multiple functions: sleeping, working, eating, exercising, medical care, maintenance, recreation. Each function has different requirements for noise, lighting, privacy, and cleanliness. On Earth, these functions are distributed across buildings and spaces. On Mars, they coexist within a small volume. This forces compromises. Noise from equipment may intrude on rest. Odors may linger. Privacy may be limited. Design must mitigate these issues as much as possible, but it cannot eliminate them entirely. Psychology becomes architecture. Power underpins everything. Mars habitats require continuous power for life support, heating, lighting, communication, and food production. Solar power is abundant but inconsistent. Dust storms reduce output. Panels degrade over time. Energy storage becomes critical. Batteries add mass and degrade. Nuclear power offers stability but introduces political, technical, and safety considerations. Power systems must be redundant, reliable, and repairable. A power failure on Earth is an inconvenience. On Mars, it is a countdown. Building on Mars also means building for maintenance. Machines will fail, parts will wear, seals will degrade, filters will clog. Habitats must be designed so that crews can access, repair, and replace components without compromising pressure or safety. This means modular systems, clear labeling, standardized parts, redundant pathways. Maintenance is not an afterthought. It is a core function of daily life. Crew members become caretakers of their environment. They must understand systems deeply. They must notice subtle changes, a strange noise, a slight odor, a temperature fluctuation. Early detection prevents catastrophe. This constant attention can be mentally taxing. Design must reduce cognitive load wherever possible. Mars habitats must also evolve over time. The first structures will be small and utilitarian. As missions expand, habitats may need to grow. New modules may be added. Systems may be upgraded. This requires compatibility and foresight. Building a world that can grow means planning for expansion before it is needed. Construction on Mars adds another challenge. Humans will not arrive with large construction crews or heavy equipment. Early habitats must be deployed robotically or assembled by small teams. Materials must be lightweight and versatile. Automated construction techniques may be required. Using local materials is appealing. Martian soil can potentially be used to make bricks or shielding. This reduces reliance on Earth shipments, but processing soil requires energy and machinery. Quality control becomes difficult. Early habitats must balance simplicity with adaptability. There is also the question of failure modes. On Earth, buildings fail gradually or catastrophically, but rescue and evacuation are possible. On Mars, failure must be managed internally. Habitats must fail gracefully. A breach in one module should not compromise the entire structure. Compartments must isolate problems. This compartmentalization affects layout, airlocks between sections, redundant pathways, emergency shelters. All add complexity and mass, yet without them, a single failure could end the mission. Building on Mars also means accepting that nothing is permanent. Structures will age faster than on Earth. Radiation degrades materials. Dust infiltrates systems. Temperature cycling causes fatigue. Habitats must be designed with limited lifespans in mind, with plans for replacement or refurbishment. This impermanence influences mission planning. How long will a habitat last? How many crews will use it? When will it need replacement? These questions affect cost and strategy. There is also a cultural dimension. The spaces humans live in shape behavior, mood, and social dynamics. A habitat is not just a shelter, it is a social environment. Its layout influences how people interact, how conflicts arise, how privacy is maintained. Design choices can encourage cooperation or exacerbate tension. Shared spaces must feel welcoming. Private spaces must feel secure. Even colour and texture matter. On Earth, architecture responds to culture. On Mars, architecture helps create culture. Mars habitats will be the first human-made environments entirely detached from Earth's ecosystems. They will be artificial worlds in the purest sense. Every element will be intentional. This is both a challenge and an opportunity. The challenge is that mistakes have consequences. The opportunity is that environments can be designed thoughtfully, based on what we know about human needs rather than historical accident. The Moon did not require this level of integration. Habitats were temporary, discomfort was accepted. Mars demands permanence of function, even if not permanence of structure. Building a world that was not built for us means acknowledging that Mars will never adapt to humans. Humans must adapt to Mars, not biologically, but technologically and socially. Every wall, every system, every routine is a negotiation with an environment that offers nothing for free. Building habitats is not just an engineering problem, it is the foundation upon which everything else rests. Exploration, science, survival, and return all depend on the success of these artificial worlds. Mars does not resist us actively, it simply does not help, and in that indifference lies the true difficulty. To live on Mars, humans must become the environment for themselves, creating stability, safety, and meaning inside structures that must perform flawlessly, not because Mars demands it, but because life does. Cost is often discussed as if it were a number that can be written down, debated, and adjusted. A budget line, a percentage of GDP, a comparison between programs. But when it comes to Mars, cost behaves less like a figure on a spreadsheet and more like a force. It stretches decisions, reshapes priorities, and quietly limits what is possible long before a rocket ever leaves the ground. Going farther does not simply cost more because the destination is distant. It costs more because distance changes everything that surrounds the journey. When humans went to the Moon, the financial burden was enormous by any reasonable standard. At its peak, the Apollo program consumed a significant portion of the United States' national budget. Entire industries were redirected. New technologies were developed rapidly, often inefficiently, because speed mattered more than optimization. That effort succeeded not because it was cheap, but because it was treated as exceptional. Mars does not benefit from that same framing. The Moon was a short, intense sprint. Mars is a long, sustained commitment, and sustained commitments are where costs grow heavy. The first place cost asserts itself is mass. In spaceflight, mass is money. Every kilogram launched from Earth must be lifted out of a deep gravity well. That requires fuel. Fuel requires tanks. Tanks require structure. Structure requires more fuel. The relationship is not linear. Small increases in mass at the destination produce large increases in mass at launch. Mars missions are burdened by this compounding effect at every stage. A Moon mission could carry just enough supplies for days. A Mars mission must carry or produce supplies for years. Extra food, extra water, extra spare parts, redundant systems, radiation shielding, exercise equipment, medical supplies. Each addition seems reasonable on its own. Together, they add up to enormous launch requirements. Reducing mass requires trade-offs. Fewer redundancies increase risk. Lighter shielding increases radiation exposure. Smaller habitats increase psychological strain. Cost is not just about money spent. It is about compromises accepted. The farther you go, the fewer compromises you can afford. Launch costs are only the beginning. Developing Mars-capable systems is expensive because they must do more, for longer, with less support. A spacecraft designed for a lunar mission can be optimized for short duration. A Mars spacecraft must endure years of operation without resupply or repair. Components must be more reliable. Testing must be more extensive. Failure modes must be anticipated. This level of reliability is costly to achieve. Testing systems for years of operation takes years. Simulating space conditions accurately is difficult and expensive. Building multiple prototypes, running long-duration tests, and validating performance under combined stresses all require time and money. Time itself is a cost. Mars missions do not fit neatly into political cycles. They require sustained funding over decades. Governments change, priorities shift, economic conditions fluctuate. A program that begins with strong support may find itself vulnerable years later when results are still distant. The Moon benefited from immediacy. Landings occurred within a decade of commitment. Mars does not offer that pace. A single human mission to Mars may take decades from initial planning to return. Maintaining financial and political support across that span is one of the largest challenges of all. Cost also accumulates in infrastructure. Mars exploration is not a single mission. It is an ecosystem of missions. Cargo launches, crew launches, pre-positioned habitats, fuel production systems, communication relays. Each element must be developed, launched, and maintained. None of these components exists in isolation. Failure in one area can jeopardize the entire effort. For example, producing fuel on Mars reduces the amount that must be launched from Earth, lowering cost in theory. In practice, it requires developing new technologies, testing them extensively, and launching additional equipment to Mars years in advance. If the fuel system fails, the crew cannot return, and the entire mission is compromised. Risk increases cost. Reducing risk requires redundancy. Redundancy increases mass. Increased mass increases launch cost. Launch cost drives budget expansion. Budget expansion increases scrutiny and resistance. This feedback loop is difficult to escape. Cost also appears in human capital. Mars missions require highly trained crews. Astronauts must be experts in engineering, medicine, geology, systems maintenance, and interpersonal dynamics. Training such individuals takes years. Keeping them trained requires continuous investment. Supporting them during and after missions adds further expense. Unlike robotic missions, human missions carry ethical obligations. Crew health must be protected. Long-term medical monitoring is required. Psychological support extends beyond the mission itself. These costs are not optional. They are part of the responsibility of sending people into extreme environments. Ground support infrastructure adds another layer. Mission control teams must operate for years, not days. Data must be analyzed continuously. Communication systems must remain functional. Software updates, navigation corrections, and contingency planning continue throughout the mission. On Earth, this requires facilities, personnel, and coordination across multiple organizations. These costs persist even when nothing dramatic is happening. Mars missions are expensive even when they appear quiet. There is also the cost of failure. A failed robotic mission is disappointing and costly. A failed human mission is unacceptable. This asymmetry drives conservative decision-making, which in turn increases development time and expense. Systems are over-tested. Margins are increased. Novel approaches are avoided. Innovation slows when failure is not an option. This is not a flaw. It is a consequence of responsibility. The Moon program accepted risks that would be unacceptable today. Some of that risk was invisible at the time. Some was knowingly accepted. Mars missions cannot rely on that tolerance. Public expectations have changed. Accountability is higher. Cost is also shaped by comparison. Mars missions are often compared to other needs: healthcare, education, infrastructure, climate mitigation. Unlike the Cold War era, Mars does not dominate geopolitical competition. It must justify itself alongside many priorities. This comparison is not inherently unfair. It reflects how societies allocate resources, but it does mean that Mars exploration must compete, not command. The Moon did not need to compete in the same way. It was framed as a singular national effort. Mars is framed as one ambitious project among many. International cooperation can spread cost, but it introduces complexity. Multiple nations bring funding, expertise, and political support. They also bring coordination challenges. Standards must align. Responsibilities must be shared. Timelines must be synchronized. Decision-making becomes slower. Cooperation reduces individual burden, but increases organizational cost. Private sector involvement offers another path. Commercial launch providers can reduce launch costs. Private investment can accelerate development, but private entities operate under different incentives. Profit motives shape priorities. Risk tolerance differs. Mars missions cannot be purely commercial. The timeline is too long. The returns are too uncertain. Public investment remains essential. This hybrid model complicates cost structures. Public and private funding must align. Responsibilities must be clear. Accountability must be maintained. Another cost often overlooked is opportunity cost. Resources devoted to Mars are resources not devoted elsewhere in space exploration. Earth observation, planetary defense, astrophysics, robotic exploration of other worlds. Budgets are finite. Choosing Mars means choosing not to do something else, at least for a time. This does not make Mars less worthy. It makes the decision heavier. Cost also manifests in patience. Mars exploration does not reward impatience. Rushing increases risk. Delays increase expense. Balancing speed and safety is costly either way. The Moon program chose speed. It paid in inefficiency and risk. Mars programs choose caution. They pay in time and sustained funding. Neither approach is free. There is also the cost of public perception. Long programs without visible milestones risk losing support. Mars missions must find ways to demonstrate progress even when major events are years apart. Robotic precursors help. Technology demonstrations help, but they require funding too. Every intermediate step costs money and attention. Cost is not static. It grows as ambitions grow. Early Mars concepts envisioned brief visits. Modern visions include long stays, permanent bases, even self-sustaining settlements. Each expansion multiplies cost. Infrastructure must scale. Life support must become more robust. Governance questions emerge. A short visit is expensive. A sustained presence is exponentially more so. This is why discussions of Mars often oscillate between bold declarations and cautious retractions. The scale of commitment becomes clear only when details are examined. It is also why timelines stretch. Mars is not delayed because people lack will. It is delayed because each step forward reveals additional costs that must be accounted for responsibly. Cost also interacts with uncertainty. Unknowns are expensive. Reducing uncertainty requires research, testing, and iteration. That research takes time and money. Some unknowns cannot be eliminated entirely. They must be accepted. Accepting uncertainty increases risk. Risk increases cost. This is another feedback loop that Mars exploration must manage carefully. The Moon program benefited from ignorance in some respects. Unknown risks were accepted because they were unknown. Mars benefits from knowledge, but that knowledge makes caution rational. Knowledge increases cost. There is also a cultural cost to consider. Mars missions require sustained focus across generations. Engineers who begin designing systems may retire before missions launch. Knowledge transfer becomes critical. Institutional memory must be preserved. Losing expertise increases cost. Rebuilding it takes time and money. This is why Mars exploration emphasizes continuity. Long-term programs, incremental development, reusable technologies. Reusability offers cost savings over time, but it requires upfront investment. Designing systems to be reused across missions increases initial cost in exchange for long-term benefit. Mars rewards this approach. The Moon did not require it. Even communication infrastructure carries cost. Mars missions require deep space communication networks capable of handling delayed intermittent signals. Antennas must be maintained, relays must be positioned, bandwidth must be managed. As missions increase, this infrastructure must scale. Scaling costs money. Cost also appears in safety margins. Every system designed for Mars includes margin, extra capacity, extra strength, extra redundancy. These margins add weight and cost. Reducing margins saves money but increases risk. Choosing margins is a value judgment as much as an engineering one. The farther you go, the harder it becomes to justify narrow margins. Mars exploration also incurs costs that are difficult to quantify. Public inspiration, scientific knowledge, technological spin-offs, cultural impact. These benefits are real, but they do not appear neatly in budgets. They are long-term and diffuse. The Moon program produced technologies that reshaped computing, material science, and engineering. Mars missions will do the same, but those returns are unpredictable and slow. This makes cost-benefit analysis challenging. Some argue that Mars is too expensive. Others argue that the cost is justified by the knowledge gained and the capabilities developed. Both views contain truth. What is clear is that Mars is not expensive simply because it is far. It is expensive because it demands completeness. You cannot send part of a Mars mission. You must send everything needed to survive, operate, and return. Partial solutions fail. The Moon allowed partial solutions, brief stays, limited infrastructure, minimal self-sufficiency. Mars does not. This difference explains much of the cost disparity. As we continue forward, this theme will remain central. Every challenge we examine, from life support to psychology to return logistics, carries a cost dimension. Decisions are constrained not just by physics, but by resources. Mars exploration is often framed as a question of capability. Can we do it? In many ways, we can. The more difficult question is whether we're willing to sustain the cost, not just financially, but institutionally, politically, and culturally, across the long span required. The Moon asks for a burst of effort. Mars asks for endurance, and endurance is always more expensive than speed. As the distance increases, so does the need for systems that last, plans that hold, and commitments that survive changing circumstances. Cost becomes not an obstacle to be overcome, but a reality to be managed, quietly shaping what goes forward and what waits. Mars does not reject us because we cannot reach it. It waits because reaching it responsibly requires accepting a price that is not paid all at once, but slowly, over years, in budgets, attention, patience, and the willingness to continue investing long after the excitement of departure has faded, carrying the effort forward until the journey finally justifies everything that went into going farther than we ever have before. Time is usually treated as something neutral, a background dimension that everything else moves through. We measure it, schedule around it, complain when there isn't enough of it. But on a journey to Mars, time stops being passive. It becomes an active constraint, one that shapes every decision long before a rocket is fueled and continues shaping outcomes long after the engines shut down. Unlike fuel, gravity, or hardware, time cannot be engineered away. It cannot be reinforced, lightened, or replaced. It simply passes at its own pace, indifferent to human urgency. And the farther from Earth a mission goes, the more power time seems to gain. The first way time asserts itself is through waiting. Mars is not always reachable. As discussed earlier, Earth and Mars move in their own orbits, opening launch windows only every couple of years. This means that even before a mission begins, time imposes patience. Plans must wait. Hardware must sit ready. Crews must train and retrain, sometimes for missions that slip repeatedly into the future. Waiting is not free. Hardware ages even when it is not used. Electronics degrade, components become obsolete, software platforms change, engineers who design systems move on. Knowledge must be transferred and relearned. Each delay introduces friction. Human factors are affected too. Astronauts selected for Mars missions may wait years before flying. Their lives continue, families change, physical condition changes, motivation ebbs and flows. Maintaining readiness over long, uncertain timelines is itself a challenge. The Moon did not impose this kind of waiting. Launch windows were frequent. Missions could be scheduled with flexibility. Mars demands alignment not just of technology and funding, but of calendars measured in planetary cycles. Once the mission begins, time stretches further. A journey to Mars takes months, not weeks, not days. Months of transit where progress is slow and incremental. The destination does not loom larger each day in a satisfying way. Instead, it grows subtly, almost imperceptibly, until suddenly it is close. This long transit changes how time is experienced. On Earth, long-term goals are punctuated by short-term milestones. On a Mars mission, milestones are spaced far apart. Launch happens, then cruise begins. For weeks, nothing outwardly changes. Systems are monitored, routines are followed. The sense of going somewhere becomes abstract. Humans are not particularly good at this kind of temporal abstraction. Motivation thrives on feedback. Mars offers little of it during transit. Time also amplifies uncertainty. Short missions can tolerate unknowns because they end quickly. Long missions must live with uncertainty for extended periods. A system that behaves oddly early in the journey may or may not fail months later. A minor medical issue may resolve or worsen over time. There is often no clear answer. Living with unresolved questions for months is mentally taxing. It creates background stress that does not peak dramatically, but also does not disappear. Then there is the time spent on Mars itself. Mars missions are shaped by orbital mechanics, not just during travel, but during stay. Once a crew arrives, they cannot leave immediately. They must wait for Earth and Mars to realign for the return journey. This waiting period can last more than a year. This means that time on Mars is not optional, it is imposed. Even if all objectives are completed early, even if conditions deteriorate, the crew must remain. The mission duration is not flexible. It is dictated by the movement of planets. This reality changes how risk is managed. On the Moon, risk could be accepted briefly. On Mars, risk must be managed over long durations. Exposure accumulates, wear accumulates, fatigue accumulates. Time turns small problems into larger ones. Consider radiation. Exposure is not a momentary event. It is cumulative. Each day adds a little more. Over months and years, this accumulation becomes significant. Shielding reduces exposure but does not eliminate it. Time ensures that whatever radiation remains will add up. The same is true for microgravity effects on the body, psychological stress and equipment wear. Time is the multiplier. Equipment is designed with lifespans. Bearings are rated for cycles. Filters are rated for hours of use. Electronics are rated for radiation dose. Mars missions push these ratings toward their limits. A system that functions perfectly for a year may fail in the second year. A component that degrades slowly may cross a threshold unexpectedly. Predicting exactly when this happens is difficult. Time makes reliability probabilistic rather than binary. This uncertainty feeds back into design choices. Systems must be overbuilt to last longer than nominal requirements. Overbuilding adds mass and cost. Cost limits how much overbuilding is possible. Again, time asserts itself quietly. Time also affects decision-making. When consequences unfold quickly, decisions can be evaluated and corrected. When consequences unfold slowly, feedback is delayed. It becomes harder to link cause and effect. A choice made today may produce consequences months later, when conditions are different and memory has faded. This delayed feedback complicates learning. On Earth, organizations learn through rapid iteration. In space, especially on Mars missions, iteration is slow. A decision made during design may not be tested until years later. If it fails, the opportunity to correct it may not come for another decade. This long feedback loop slows progress and increases conservatism. Time also interacts with human attention in important ways. Humans are good at responding to acute crises. We are less effective at maintaining vigilance over long periods. When nothing seems to be happening, attention drifts, complacency can set in. Checklists feel repetitive, alarms fade into the background. Mars missions must guard against this. Procedures must be designed to remain meaningful even when repeated daily for years. Training must reinforce not just skills, but habits of attention. Automation must assist without encouraging disengagement. This balance is difficult. If systems are too automated, humans lose situational awareness. If systems demand constant input, humans become fatigued. Time amplifies both problems. Then there is the matter of aging. Mars missions span years. Crew members will age measurably during the mission. Physical capacity changes subtly with age. Recovery from injury slows, vision changes. These changes are not dramatic, but they are real. Mars missions must account for this by selecting crews carefully and designing workloads that can be sustained over time. The same applies to mission control teams on Earth. Supporting a Mars mission is not a short assignment. It requires continuity. Teams must remain engaged and knowledgeable for years. Turnover risks loss of institutional memory. Maintaining continuity over long timescales is expensive and difficult. Time also affects technology relevance. Technological development on Earth moves quickly. By the time a Mars mission launches, some of its systems may already be outdated compared to current technology. This does not necessarily make them worse, but it complicates maintenance and upgrades. Once a mission begins, technology freezes. No upgrades, no patches beyond what was planned. Crews live with the technology they launched with, even as Earth moves on. This temporal disconnect can be psychologically strange. Messages from Earth describe a world that continues to change. New devices, new discoveries, new events. The crew remains embedded in an earlier technological moment. This reinforces the sense of separation. Time also affects risk perception. Short missions encourage risk-taking. If something goes wrong, consequences are limited. Long missions encourage caution. Consequences stretch out. Recovery takes longer. Mistakes linger. Mars missions naturally adopt a conservative posture. This is not due to fear, but to arithmetic. When the timeline is long, the cost of error increases. This conservatism frustrates some observers. Progress feels slow. Milestones feel distant. But this slowness is a response to time as an obstacle. Time also affects public engagement. Public attention is not designed for multi-decade projects. Interest peaks around launches and landings, then fades. Sustaining support over long periods requires deliberate effort. Outreach, education, intermediate achievements. Each of these efforts consumes resources. The Moon benefited from frequent visible milestones. Mars offers fewer of them. The waiting periods are longer. The payoffs are delayed. Time challenges narratives. It is easy to tell a story about a race. It is harder to tell a story about endurance. Mars exploration is an endurance story. It unfolds slowly. Progress is incremental. Setbacks occur quietly. Time makes it harder to maintain momentum. There is also the personal time cost to consider. Astronauts commit years of their lives to a Mars mission. Training alone may take a decade. The mission itself may take several years. Recovery and reintegration add more time. This is a profound commitment. It affects families, careers, and identities. Not everyone is willing or able to make it. This limits the pool of candidates and increases the importance of selection. Time also affects health outcomes. Long-term exposure to stressors increases uncertainty in medical predictions. We can estimate radiation risk, but individual susceptibility varies. We can model muscle loss, but individual adaptation differs. Time introduces variability that cannot be eliminated. This uncertainty complicates ethical decision-making. How much risk is acceptable over years? How much uncertainty can be justified? These questions do not have simple answers. Time also interacts with failure modes. In short missions, failures tend to be obvious. A system fails and is noticed. In long missions, failures can be gradual. Performance degrades slowly. Thresholds are crossed quietly. Detecting slow failures requires monitoring and trend analysis. Crews must notice subtle changes and act before problems become acute. This demands sustained attention and expertise. Time tests discipline. There is also the issue of synchronization. Mars missions operate on multiple clocks simultaneously. Earth time, Mars time, spacecraft time. Communication delays create temporal offsets. Schedules must account for these differences. Mars days are slightly longer than Earth days. Over time, this difference accumulates. Crews may shift their schedules relative to Earth. Coordination becomes complex. Time zones on Earth are trivial by comparison. Time also affects science. Many scientific objectives on Mars require long-term observation. Seasonal changes, atmospheric dynamics, geological processes. These unfold over months and years. Rushing misses patterns. Time enables deeper understanding, but only if systems and crews can endure. This is a paradox. Time is both an obstacle and a resource. The Moon allowed us to ignore time in some respects. Missions were short, effects were contained. Mars forces us to engage with time directly. We must plan for it, design for it, live with it. This requirement reshapes how we think about exploration. Mars is not a place you visit briefly. It is a place you commit to experiencing over a long arc. This commitment extends beyond any single mission. Knowledge gained from one mission informs the next. Infrastructure may persist for decades. Decisions made early echo forward. Time links missions together. This is why Mars exploration is often described as a program rather than a mission. It unfolds across generations. It requires continuity of purpose. Time also reframes success. Success is not just landing or returning. It is sustaining capability, maintaining health, preserving systems, learning gradually. These are slow victories. The Moon allowed us to celebrate discrete achievements. Mars demands appreciation for processes. Time will remain a central theme. It influences psychology, cost, risk, and design. It cannot be ignored or compressed. Mars does not defeat us by being far. It challenges us by being patient. It moves at its own pace. Its seasons are long. Its storms linger. Its distances stretch journeys into months. Its return windows wait years. To go to Mars is to accept that time is no longer something we control. It is something we negotiate with. And in that negotiation, success depends not on speed or urgency, but on endurance, consistency, and the willingness to work within timelines that do not bend to human impatience, carrying the effort forward slowly, steadily, and deliberately until progress emerges not as a sudden leap, but as the accumulated result of respecting time as the most subtle, persistent obstacle of all. Before humans ever attempt to endure the long journey, the waiting, the isolation, and the commitment that Mars demands, machines have already been there, quietly doing the work of exploration without ceremony or applause. These machines did not go first because humans lacked courage. They went first because Mars required learning at a distance, and robots tolerate distance better than we do. The story of Mars exploration is, in many ways, the story of these robotic pathfinders. Each one arrived alone. Each one faced the planet without rescue, without companionship, and without the expectation of return. They were designed to survive as long as possible, learn what they could, and then fail gracefully when the environment finally won. In doing so, they taught us what Mars is actually like, not as a symbol, but as a place. The earliest robotic visitors to Mars were blunt instruments by today's standards. They were not agile. They were not autonomous in any meaningful sense. They were designed simply to arrive, function briefly, and transmit whatever data they could before inevitably falling silent. Even that proved difficult. Many early attempts never made it to the surface at all. Entry, descent, and landing failures were common. Communication was lost. Signals faded. Mars earned a reputation as a place where missions disappeared without explanation. These failures were frustrating, but they were also informative. Each one revealed something about what Mars demanded. Eventually, landers began to succeed, if only briefly. Fixed platforms touched down and transmitted images and measurements. They confirmed what telescopes had suggested. Mars was cold, dry, thin-aired. Its surface was shaped by forces that once involved water, but no longer did so in obvious ways. Then came mobility. When the first rover, Sojourner, rolled onto the Martian surface, it changed the nature of exploration entirely. Sojourner was small, slow, and limited, but it could move, it could choose targets, it could approach rocks rather than simply observe whatever happened to be nearby. This shift from stationary observation to active exploration was subtle, but profound. Mobility revealed complexity. Mars was not uniform. Its surface varied over short distances. Rocks differed in composition. Terrain shifted from smooth plains to jagged outcrops. Dust behaved differently depending on location. Temperature varied with slope and shadow. A single landing site could not represent the whole planet. As rover technology improved, missions grew bolder. Twin rovers, Spirit and Opportunity, were designed for relatively short missions. They were expected to operate for about 90 Martian days. Instead, they endured for years. This endurance was not planned. It emerged from careful design, cautious operation, and a measure of luck. These rovers revealed Mars as a planet with a deep and complex history. They found minerals that form in water. They documented ancient environments that were once wet, possibly habitable. They also demonstrated how slowly Mars wears down machines. Wheels eroded. Solar panels accumulated dust. Instruments degraded. Each failure was gradual. Each one taught engineers how Mars interacted with hardware over long periods. These lessons mattered because they shifted expectations. Mars was not a place where machines failed quickly and dramatically. It was a place where they wore down slowly. This slow degradation mirrors what human systems would face. Later rovers increased in size, capability, and ambition. Curiosity arrived, carrying a laboratory. It could drill into rock, analyze samples, and assess habitability directly. It required a completely new landing system, one that involved hovering on rocket engines and lowering the rover on cables. That landing system worked once. That was enough to prove the concept, but not enough to make it routine. The complexity involved underscored how difficult Mars remains, even for machines. Curiosity's longevity demonstrated something else as well. Given sufficient robustness and careful operation, machines could function on Mars for many years, but they required constant attention. Engineers on Earth planned each day's activities carefully, accounting for power levels, temperature, terrain, and communication constraints. Mars demanded patience even from robots. As missions progressed, autonomy increased. Rovers gained the ability to navigate around obstacles, choose paths, and manage power more intelligently. This autonomy was not about convenience. It was a necessity imposed by communication delays. Earth could not joystick a rover in real time. Decisions had to be made locally. This local decision-making foreshadowed what human crews would eventually need to do. The most recent rovers brought this idea further. Perseverance was designed not just to explore, but to prepare for human arrival. It collected samples intended to be returned to Earth in the future. It tested technologies relevant to human missions, including oxygen production from the Martian atmosphere. This was a critical shift. Robots were no longer just scientists. They became scouts and engineers, evaluating whether human survival systems could function at all. Perseverance carried with it a small companion, Ingenuity, a lightweight helicopter designed to test powered flight in Mars's thin atmosphere. Against expectations, it flew, again and again. Each flight was brief and modest, but together they demonstrated that new modes of mobility were possible. This mattered because it expanded the toolbox. Aerial reconnaissance could support future missions, terrain could be assessed more efficiently, hazards could be avoided. Robots were not just learning about Mars, they were changing how exploration could happen there. Despite these successes, robots also revealed limits. Machines do not experience fatigue, fear, or loneliness, but they also do not improvise the way humans do. When confronted with unexpected situations, robots rely on pre-programmed responses. When those responses are insufficient, progress slows. Many rovers have become trapped, immobilized by soft soil or unexpected slopes. Engineers have spent months, sometimes years, coaxing machines free through careful commands. These struggles highlighted how unpredictable Mars terrain can be. If a robot can become stuck permanently, so can a human vehicle. Robots also highlighted the importance of maintenance. Wheels wore down, drills jammed, sensors failed. Repairs were limited to what could be done remotely. When a component failed beyond repair, the mission adapted or ended. Humans would face similar challenges, but with higher stakes. A broken drill for a robot means reduced science. A broken life support component for humans means crisis. Robots taught us which failures were tolerable and which were not. Another lesson robots delivered was about time. Robotic missions unfold slowly. Each command sequence is planned, transmitted, executed, and reviewed. Days or weeks pass between major actions. This pace mirrors the pace humans would experience on Mars, where rushing increases risk. Mars rewards deliberation. Robots also taught us about Mars's unpredictability. Dust storms reduce power unexpectedly. Temperature swings affected instruments. Mechanical parts behave differently over time than models predicted. Each surprise refined understanding, but also reinforced humility. Mars does not behave exactly as simulations suggest. Perhaps most importantly, robots taught us about limits of presence. Robots can survive in environments humans cannot. They tolerate radiation without fear. They do not require breathable air. They can endure isolation indefinitely. This makes them ideal explorers. But robots cannot replace humans entirely. They cannot make intuitive leaps. They cannot notice subtle patterns without being programmed to do so. They cannot repair complex systems creatively. This balance has shaped exploration strategy. Robots go first to reduce unknowns. Humans follow only when the environment is understood well enough to support life. Robots also revealed something about commitment. Each robotic mission represents years of work and billions in investment, yet they are accepted as potentially expendable. Failures are tragic but tolerable. Data loss is disappointing but survivable. Human missions cannot be treated this way. This asymmetry forces caution. Robots can be risked to learn. Humans cannot. The robotic pathfinders also demonstrated how Mars exploration accumulates knowledge. No single mission answers everything. Each one builds on the last. Landing techniques improve, navigation improves, power systems improve, autonomy improves. This cumulative progress is slow, but it is real. Robots have mapped radiation levels, measured dust behavior, tested materials, analyzed soil chemistry, studied weather patterns. Every data point reduces uncertainty for future missions. Mars is not becoming easier. We are becoming better informed. There is also an emotional dimension to robotic exploration that is easy to dismiss but difficult to ignore. People form attachments to these machines. They follow their journeys. They mourn their losses. When a rover goes silent after years of service, it feels like the end of a relationship. This response may seem irrational, but it reflects something deeper. Robots are our proxies. They experience Mars on our behalf. They send back images and data that allow us to imagine being there. They extend human curiosity into places we cannot yet survive. This proxy relationship matters. It builds public engagement. It sustains interest over long timelines. It creates a sense of continuity. Robots also serve as ethical buffers. They allow us to explore without risking human life prematurely. They force us to confront the environment honestly before committing people to it. This is not hesitation. It is responsibility. As robotic missions become more capable, the line between robotic and human exploration begins to blur. Robots test technologies humans will rely on. They prepare landing sites. They assemble infrastructure. They scout resources. Some future concepts even envision robots building habitats before humans arrive, constructing shelters, laying foundations, and preparing systems. In this vision, humans do not arrive as pioneers carving a path. They arrive as residents entering a space already shaped by machines. This inversion of historical exploration patterns reflects Mars's demands. Mars does not allow gradual human encroachment. It requires preparation at scale. Robots also expose one of the central challenges of Mars exploration. Success does not look dramatic most of the time. It looks like routine, data collection, maintenance, incremental progress. This can feel unsatisfying to those expecting spectacle, but it is precisely this quiet competence that enables long-term success. Mars exploration has never been about a single moment. It has always been about endurance. The robots that went first demonstrated endurance without complaint. They worked day after day, year after year in conditions that would kill humans quickly. They did so because they were designed to. Humans are not designed that way. We require comfort, connection, and care. We require environments shaped to our needs. Robots revealed how far Mars is from meeting those needs naturally. At the same time, robots revealed that Mars is not entirely hostile. Systems can function there. Machines can operate. Resources exist. Water ice is present. Oxygen can be extracted. Structures can endure. Mars is not impossible. It is conditional. Robots helped us understand those conditions. As we move forward, the role of robots will not diminish. They will continue to precede humans, accompany them, and support them. Human missions will depend on robotic systems for scouting, maintenance, and logistics. This partnership is not a stepping stone to replacement. It is a recognition of complementary strengths. Robots go first because they can fail without tragedy. Humans follow only when failure has been reduced to something survivable. The Moon did not require this level of robotic preparation. Mars does. This is why, when we ask why Mars is so much harder, the answer is not simply distance or danger. It is the accumulation of lessons delivered patiently by machines that endured Mars long before we ever considered asking humans to do the same. Those machines did not complain about the cold, the dust, or the silence. They simply reported it, data packet by data packet, slowly replacing speculation with understanding. And as that understanding deepens, it becomes clear that robots were not merely precursors. They were translators, converting an alien environment into something we could begin to reason about. They went first not to conquer Mars for us, but to teach us what kind of place it is. And in doing so, they quietly set the terms under which humans might one day follow, not as conquerors or visitors, but as cautious participants in a world that revealed itself only to those willing to wait, observe, and learn from machines patient enough to survive where we cannot yet stay. Mars does not ask for bravery in the way stories often frame it. It does not respond to bold gestures or dramatic declarations. It does not reward speed, confidence, or force of will. What Mars demands is quieter, heavier, and harder to sustain. It demands consistency. It demands humility. It demands that humans accept limits they are not used to accepting, and then work patiently within them. The first thing Mars demands is preparation that borders on excess. On Earth, preparation is often balanced against improvisation. If something goes wrong, people adapt. Resources can be redirected. Help can be summoned. On Mars, improvisation exists, but only within narrow boundaries. The environment does not provide slack. There is no hidden reserve of oxygen, water, or shelter to fall back on. This means that Mars demands preparation not just for what is likely, but for what is merely possible. Every system must assume that it will be stressed. Every component must assume that it will age. Every plan must assume that something will fail at the worst possible time. This mindset runs counter to how many complex projects are managed on Earth, where efficiency and cost reduction often take precedence. Mars does not tolerate efficiency that comes at the expense of resilience. This requirement reshapes engineering culture. Designs must favour reliability over elegance. Proven technologies are often chosen over cutting-edge ones. Redundancy is not a luxury, it is a baseline expectation. Mars also demands patience. Not symbolic patience, but operational patience. The willingness to wait for launch windows. The willingness to delay missions rather than accept unacceptable risk. The willingness to move slowly on the surface, even when progress feels frustratingly incremental. This patience can be difficult to justify publicly. From the outside, delays look like indecision. Caution looks like lack of ambition. But Mars does not reward haste, it punishes it. The planet moves on its own schedule. Its orbits open and close opportunities. Its storms arrive and linger. Its seasons unfold slowly. Humans cannot negotiate with these rhythms, they must align with them. Mars also demands collaboration on a scale that exceeds most previous exploration efforts. No single nation can easily shoulder the burden alone. The technical challenges are broad, the costs are sustained, the expertise required spans disciplines and institutions. Cooperation becomes less a political gesture and more a practical necessity. But cooperation brings its own demands. Standards must be shared. Data must be trusted. Responsibilities must be clear. Decisions must account for multiple stakeholders. This slows progress, but it also stabilizes it. Mars demands that humans work together even when incentives differ, even when timelines stretch beyond election cycles and corporate planning horizons. It demands institutional endurance. Mars also demands honesty. It demands honest assessments of risk, honest communication about uncertainty, honest acknowledgement of what is not yet known. Overconfidence is dangerous. Simplified narratives are misleading. Mars missions require transparent discussion of trade-offs. How much radiation exposure is acceptable? How much isolation is tolerable? How much redundancy is enough? These are not questions with perfect answers, but they must be confronted openly. Mars does not tolerate denial. Another demand Mars places on us is adaptability. Even with extensive preparation, Mars will surprise us. Equipment will behave in unexpected ways. Environmental conditions will differ from models. Human responses will vary. Adaptability does not mean improvising wildly. It means designing systems and procedures that can accommodate variation without collapsing. It means training crews to respond thoughtfully rather than reflexively. It means empowering decision-making at the point of action rather than relying exclusively on distant authority. Mars demands trust in human judgment, supported by structure rather than constrained by it. Mars also demands restraint. Not every technological capability should be used simply because it exists. Not every risk should be taken because it is technically possible. Mars missions must resist the temptation to push boundaries unnecessarily. This restraint can feel counterintuitive in exploration, which is often associated with pushing limits. But Mars exploration is not about seeing how much humans can endure. It is about sustaining presence long enough to learn and return. Mars demands that we stop equating suffering with achievement. It also demands respect for the human body and mind. Long-duration missions expose humans to conditions they did not evolve to tolerate. Radiation, isolation, confinement, altered gravity, and prolonged stress all interact in complex ways. Mars does not forgive neglect of these factors. Crew selection must prioritize psychological resilience alongside technical skill. Mission design must protect mental health as actively as physical health. Rest, privacy, communication, and meaning must be treated as mission critical. Mars demands that we take human needs seriously, even when they complicate engineering. It also demands foresight. Decisions made early will echo forward. Choosing a landing site influences future expansion. Selecting one power system over another shapes infrastructure. Designing habitats for short-term use limits long-term options. Mars does not offer easy do-overs. Each mission builds on the last. Mistakes compound. Successes create momentum. This makes foresight a moral responsibility as well as a practical one. Mars also demands acceptance of vulnerability. On Earth, vulnerability is often hidden. Systems fail quietly, buffered by scale and redundancy. On Mars, vulnerability is visible. The thinness of the margin between survival and catastrophe is ever present. This awareness can be unsettling. It strips away illusions of control. It forces reliance on others. It requires trust in systems and people. Mars demands that humans accept that they are not self-sufficient as individuals. Survival is collective. Mars also demands discipline. Routine matters. Procedures matter. Small deviations can accumulate into serious problems. Attention to detail is not optional. Complacency is dangerous. This discipline must be sustained not for hours or days, but for years. It must persist even when nothing dramatic is happening, especially then. Mars rewards steady competence, not flashes of brilliance. It also demands learning. Every mission will encounter unknowns. The ability to observe, analyze, and adjust based on experience is essential. Mars missions cannot rely solely on pre-written plans. They must incorporate feedback continuously. This requires a culture that values learning over blame. When something goes wrong, the question must be, what can we understand, not who failed? Mars demands maturity in how humans approach failure. Mars also demands clarity of purpose. Why are we going? What are we trying to achieve? Scientific discovery, technological development, long-term survival of human civilization, inspiration. These motivations are often cited, but they must be translated into concrete objectives. Ambiguity breeds conflict. Clear goals align effort. Mars missions are too costly, too risky, and too long to sustain without shared purpose. Mars also demands long-term thinking beyond individual missions. If humans are to go to Mars responsibly, it cannot be a one-off spectacle. It must be part of a sustained program. Infrastructure must be reusable. Knowledge must be preserved. Lessons must be integrated. This demands continuity across generations of engineers, scientists, and leaders. It demands institutions that outlast individual careers. Mars does not fit into short-term thinking. Mars also demands ethical reflection. Sending humans to Mars exposes them to significant risk. Those risks must be justified. Consent must be informed. Support must be comprehensive. Post-mission care must be provided. Mars missions raise questions about responsibility that cannot be answered purely by technical feasibility. Just because we can attempt something does not automatically mean we should, or that we should do so in any particular way. Mars demands ethical seriousness. It also demands humility in how we interpret success. Success on Mars may not look dramatic. It may look like systems working quietly, like crews returning safely, like data collected methodically, like incremental improvements. Mars does not need to be conquered to be understood. It does not need to be transformed to be valuable. Mars demands that we let go of conquest narratives and replace them with stewardship narratives. Mars also demands realism about limits. There are things Mars will not allow. It will not allow quick rescue. It will not allow error without consequence. It will not allow shortcuts to self-sufficiency. Accepting these limits does not diminish ambition. It grounds it. Mars exploration is not about proving that humans are invincible. It is about proving that humans can plan, cooperate, and endure responsibly. Mars also demands that we rethink what progress looks like. Progress is often measured by speed. How quickly can we get there? How fast can we build? How soon can we return? Mars reframes progress as reliability. Can we stay alive? Can we learn? Can we leave safely? This reframing is uncomfortable but necessary. Mars also demands emotional honesty. There will be moments of fear, doubt, homesickness, fatigue. Acknowledging these does not weaken missions, it strengthens them. Ignoring them creates blind spots. Mars missions must normalize emotional experience rather than suppress it. Mars demands trust in process. Because outcomes unfold slowly, faith in process becomes essential. Crews must trust that preparation matters. Engineers must trust that testing matters. Institutions must trust that patience matters. Mars does not provide immediate feedback. Trust bridges the gap. Mars also demands acceptance of uncertainty. Not everything can be predicted. Not everything can be controlled. Risk can be reduced, but never eliminated. Living with this uncertainty without becoming paralyzed is a skill that Mars demands. This skill applies not just to crews, but to societies supporting the missions. Mars exploration is not a single challenge. It is an accumulation of many challenges that interact over time. What Mars demands of us is not heroism in the traditional sense. It demands reliability, cooperation, humility, endurance, care. These qualities are less dramatic than flags and footprints, but they are more difficult to sustain. The Moon allowed us to arrive, accomplish a goal, and leave. Mars demands that we arrive prepared to stay longer than is comfortable, to work methodically, and to leave only when the planet allows it. In this sense, Mars is not testing our technology as much as it is testing our values. Are we willing to prioritize safety over spectacle, preparation over speed, collective success over individual achievement? Mars demands that we grow into the kind of explorers who can live with consequences rather than chase moments. It becomes clear that Mars is not just a destination. It is a mirror. It reflects back how seriously we take responsibility, how we handle limits, and how willing we are to commit to something that unfolds slowly, without guarantees. The difficulty of Mars is not a flaw to be overcome. It is a condition to be respected, and in respecting it, we may find that what Mars demands of us is not simply more advanced machines, but a more deliberate, patient, and thoughtful version of ourselves, capable of carrying effort forward not in bursts of excitement, but in steady, careful steps that acknowledge how far we have come, how far we still are, and how much it matters that when we finally do go, we do so with the discipline and care that such a demanding world requires. The horizon on Mars does not rush toward anyone. It sits where it is, distant and unchanged, no matter how many times it's photographed, mapped, or imagined. From orbit, it curves gently beneath a thin sky. From the surface, it stretches flat and wide, coloured by dust and filtered light, offering no immediate promise beyond what is already visible. It is a horizon that does not invite pursuit so much as it waits. That waiting is not passive. It is a consequence of everything that Mars is. For decades now, humans have known how to reach the vicinity of Mars. We have sent orbiters, landers, rovers, and flying machines. We've studied its chemistry, its weather, its radiation, and its history. We have proven again and again that Mars is accessible in principle, and yet despite all of this, the horizon remains untouched by human presence. This is not because the path is unknown. It is because the path is demanding in a way that resists shortcuts. When people ask why Mars is so much harder than the Moon, they often expect a single answer: distance, gravity, atmosphere, radiation, cost, time. Each of these is true, but none of them alone explains the delay. Mars is harder not because of one overwhelming obstacle, but because of how many ordinary challenges persist simultaneously, without relief, and for so long. Mars is not dramatic in the way popular imagination sometimes expects. It does not greet explorers with violent storms or towering mountains that must be conquered immediately. Instead, it applies steady pressure, it erodes systems, it accumulates wear, it stretches timelines, it forces attention to detail, it punishes complacency quietly. The Moon allowed humanity to act quickly. Missions were short, risks were contained in time, discomfort was tolerated because it was temporary. Mars removes that option. Nothing about a Mars mission is temporary in the way we're used to. This changes how decisions feel. On Earth, and even in lunar exploration, decisions can be framed as reversible. Mistakes can be corrected later. Plans can be adjusted. On Mars, reversibility fades. Once a mission is underway, choices carry long consequences. Once a crew arrives, they are committed to a duration dictated by planetary motion, not human preference. That commitment alters the meaning of arrival. Reaching Mars is not the end of a journey. It is the beginning of an obligation to remain functional, to remain healthy, to remain cooperative, to remain patient. Leaving is not an immediate option. Success depends not on a moment of triumph, but on endurance. This is why the red horizon still waits. Every challenge discussed so far feeds into this moment of waiting. Distance delays, rescue, time stretches exposure, dust degrades systems, radiation accumulates, psychology becomes as important as engineering, cost demands sustain support, entry and landing compress risk into minutes that allow no correction. None of these problems is unsolved, but none of them is solved well enough simultaneously to justify placing human lives at their intersection without hesitation. Mars is unforgiving of partial readiness. Robotic missions can accept partial success. A rover that loses a wheel can still do science. A lander that tilts can still transmit data. Human missions cannot tolerate such compromises. A habitat that leaks slightly is not mostly successful. It is dangerous. A power system that underperforms is not inconvenient. It is life-threatening. This difference is crucial. The robots that went first were allowed to fail because failure taught us something. Humans cannot be sent with the same expectation. The standard for readiness must be higher, not because humans are more valuable than machines, but because the consequences are irreversible. Mars does not grant second chances easily. There is also the matter of scale. Going to the Moon required extraordinary effort, but it was focused. A narrow goal, a limited duration. Mars requires a broader vision. Not just how to get there, but how to live there long enough to leave safely. That requires systems that work together over years. It requires planning beyond a single mission. This scale amplifies everything. Costs are not paid once, they are paid repeatedly. Training does not end at launch. Support does not end at landing. Responsibility does not end at return. Mars missions extend across entire careers, sometimes across generations. The horizon waits because this scale cannot be rushed into existence. There is also a cultural component that is easy to overlook. The moon landings occurred in a moment when speed mattered more than sustainability. The goal was singular and symbolic. Mars exploration does not occupy that same cultural position. It must justify itself continuously. It must compete with other priorities. It must explain delays rather than hide them behind urgency. This environment rewards caution, not spectacle. Mars does not benefit from a race. It benefits from accumulation, from testing, from iteration, from patience. That patience can be frustrating. It can feel like stagnation. But it is, in many ways, a sign of maturity. Early space exploration often accepted unknown risks simply because they were unknown. Today, we know more. That knowledge does not make Mars easier. It makes caution unavoidable. Knowing what could go wrong forces responsibility. This responsibility is part of why the horizon remains unbroken by footprints. Not because humans are incapable, but because they are aware. Mars has taught us that awareness is not paralysis. It is preparation. Every robotic mission refines models. Every test improves systems. Every delay resolves an uncertainty. Progress on Mars is not measured in launches alone. It is measured in confidence earned slowly. The horizon waits while confidence accumulates. There is also a psychological truth embedded in that waiting. Humans are accustomed to goals that move closer as effort increases. Mars resists this feedback. Years of work may not bring visible proximity. The horizon looks the same from afar. This can be discouraging. But this appearance is deceptive. Behind the scenes, infrastructure grows, knowledge deepens, capabilities align. What looks like stillness is often consolidation. Mars does not reward impatience with progress. It rewards patience with readiness. The red horizon is not a taunt. It is a boundary that marks where ambition must meet discipline. When humans finally do stand on Mars, the moment will not represent victory over the planet. It will represent agreement with it, an agreement to operate within its limits, to respect its conditions, to accept that survival there depends on ongoing effort, not a single achievement. That agreement must be honoured every day the crew remains. This is why Mars is harder than the Moon. The Moon allowed humans to arrive briefly, accomplish a goal, and depart before systems degraded and psychology strained. Mars insists that arrival is only the beginning. It insists that systems must last, that people must adapt, that planning must extend far beyond the landing. Mars does not resist us violently. It resists us through persistence. The horizon waits because persistence takes time to match. There is also something quietly appropriate about this. Mars is a planet with a long history. Its surface preserves billions of years of change. It has waited through epochs without atmosphere thickening, without oceans returning, without life reasserting itself in obvious ways. A few decades of human delay are insignificant on that timescale. Mars is not in a hurry. That does not mean the effort is wasted. Every year of preparation reduces risk. Every mission clarifies reality. Every delay reflects a choice to value safety over haste. When humans do go, they will not go because they were finally brave enough. They will go because the conditions for sustained survival have been met well enough to justify the attempt. Until then, the red horizon remains where it has always been. Distant, unchanged, patient. It waits not because Mars is unreachable, but because Mars demands a kind of readiness that cannot be improvised. A readiness that emerges only after technology, psychology, institutions and values align. That alignment is slow. And perhaps that is the final lesson hidden in the waiting horizon. Mars is not teaching us how to travel farther. It is teaching us how to commit longer, how to plan deeper, how to accept that some destinations are not meant to be rushed toward, but approached carefully, with respect for what they require and honesty about what they cost. The Moon showed us that we could leave Earth. Mars is showing us that leaving Earth responsibly is harder than it looks. So the horizon waits. Not as a challenge issued, and not as a promise withheld, but as a reminder that the difficulty of Mars is not an accident. It is the natural consequence of trying to bring fragile human life into a place that does not offer forgiveness for impatience. When the time comes and humans finally move past that waiting line, it will not feel like a sudden leap. It will feel like the continuation of a long process that has been unfolding quietly all along, carried forward by machines, by planning, by restraint, and by the decision to let the horizon wait until we are ready to meet it, on terms that allow us not just to arrive, but to endure beyond arrival, keeping the story moving forward rather than ending it where the red landscape begins.